You're live now.
All right, welcome everyone. I'm excited to begin our first Wolfram Institute workshop, which happens to be dedicated to hypermatrices. Um, my name is James Douglas Boyd. I'm the CEO of the Wolfram Institute. We're a nonprofit research organization that was co-founded last year. Stephen Wolfram and I co-founded it together. And I think that this particular workshop, which was suggested by Carlos Zapata, one of our Institute fellows, and both addresses and generalizes many of the research areas that pique his interest and that he's pursuing while at the Institute. I'd like to think that this particular workshop that we're going to present to you all, actually over the course of this entire week, with engagements that are both publicly broadcasted as well as held privately between individuals who both wanted to geek out about hypermatrices. I'd like to think that this event does, in some sense, capture one of the goals that motivates and guides the Institute, and that is the use of computation to advance the mathematical sciences, especially along particular trajectories that are kind of either slightly overlooked or slightly underdeveloped. I think that the the hypermatrix is kind of a good example of this. Carlos certainly has much to say about the research that he's been doing. He's not necessarily the protagonist of this week, though he is the kind of the MC and the host. So maybe without further ado, I'll defer to Carlos to describe in greater detail this workshop that he has both suggested and also capably helped to wrangle together. So anyway, we go to you live from Alicante, Spain, which has good food and also ideas of a higher arity future. Carlos, without further ado, the floor is yours.
Well, thank you very much, James, for that introduction, and welcome everyone to the HyperMatrix workshop this week. I'm very pleased to have finally made this public and be able to go live with the event because, as James said, I mean, when I joined the Wolfram Institute, I was thinking this kind of strange research that I'm getting myself into doesn't fit very well anywhere. Obviously, there are themes around, but doesn't fit very well anywhere. And I was able to continue working within the institute. So it's great to have this material representation in this workshop. So in terms of the contents of the workshop, I'm very excited to actually show you. Maybe I can share very briefly this screen to show the program. And so you can see that we have quite a widespread of subdisciplines that touch upon hypermatrices and higher order structures and so on. Unfortunately, Richard Kerner, who many of you might know, wrote some influential physics papers in the late 90s, early 2000s, cannot make it. He sent an email today saying that, so the slot on Friday was going to be him, but he cannot make it, unfortunately, because he's traveling in Brazil. But other than that, I think we've gathered a good hypergraph of speakers and topics. So I'm quite excited to be hosting this and to be able to actually interface with many of you. I mean, I've read many papers that have your names as in the author list, and I'm quite happy to see you here live. So that's always exciting. Other than that, I just want to announce that this is there's a Monday and Friday, so bookend events that we're doing live, and then during the week we hope that we can freely exchange emails. You can come over to the Discord to have informal chats via text, and then this room will always be available. So if we want to hop on and share some virtual Blackboard and do some work, that's always a possibility. So yeah, I thought that maybe because some of our speakers are already present here, we can do some brief introductions so we all know each other. So maybe Tali, Luke, and Josh, you can go ahead and introduce yourselves.
Hi, I'm Tally. Carlos and I are collaborators as of about a year ago. And my background is I did an undergraduate math and physics, joined industry, found myself at Wolfram within a year or two, which was like a nice mix of math and comp sci. And after a couple of years there, ended up working on the deep learning framework in Mathematica. I led the team that implemented that, and left a few years ago to just kind of read and study new things and kind of, yeah, continue my journey. And yeah, recently became very interested in hypergraphs and high arity arrays, and that's what Carlos and I have worked on. Yeah.
Thanks, Ali. Luke?
Hey guys, I'm Luke Oding. I'm at Auburn University, which is in Alabama, in the south of the U.S. My student is here, Matt Speck, so you can wave. I advertise to my colleagues at Auburn. Yeah, thanks for the invitation to speak on the workshop. I've been working on tensors for most of my career. I've found connections to computer vision and quantum information most interesting recently, but always at the background is some sort of computation with algebra and symmetry and representation theory. I've used Mathematica for some crucial computations. I use Maple very often. I also use Macaulay too, because each of them have features that either I know how to use or happen to be better. And so anyway, I'm happy to participate in this, and I'm looking forward to lots of cool interactions. I have to apologize. I have to teach in my time zone. It'll be 1 o'clock, so right before I give my talk. So I will do my very best to be back here on time. And Josh, I'll miss your talk, but sorry about that.
No problem. We'll wait for you.
Yeah.
Thanks, Luke. Josh?
Hi, everyone. I'm Josh Grochow. I'm at University of Colorado Boulder. Yeah, I don't know. I similar to Luke, I think I've been kind of working on tensors for most of my career, although I've been coming at it more from the computer science angle. Still a lot of math involved, and Luke and I have some overlaps in the past, but yeah, definitely more from the CS angle. But yeah, it wasn't until maybe about a decade ago that I started seriously thinking more generally about higher arity structures in general and relations between different structures. And yeah, so I was very happy when I saw this workshop and got invited, that like, oh, hey, you know, like you were saying, Carlos, it's like there's this whole community of people that also are thinking about these higher arity things. And yeah, so I'm very excited to see what the week brings.
Amazing. Well, as Josh said, this was the opportunity for me to gather these people around, and it's been a couple of years since I've been involved in this high arity research, and it's been strange because you don't assign this topic to a single branch, and so it's hard to just go, oh yeah, this is in this department, there's a group working on this, and then you find the people that, you know, I've talked to physicists, I've talked to computer scientists, I've talked to pure mathematicians, I talked to biologists, I've talked to all kinds of people who are, you know, very firmly interested in these kinds of ideas, and they don't happen to be under one single dome, which is, I think, more of a boon than a limitation. So very happy to get things started. So without further ado, maybe we can pass it over to Tali and start to hear about rainbow arrays.
Hello, thanks. Let me share my screen.
Yep, all good.
Okay. Everyone see?
Yep.
Awesome. Yeah, I'm going to try to just shrink this little video panel if I can. Yeah, that's good. Cool. So yeah, rainbow arrays is just like a cute name that I came up with for to describe a sort of bit of a sea change that's happening in the world of array programming, which is the primary way that I've come to think about arrays and tensors, although I'll distinguish those obviously. So I want to communicate my particular take on this, my flavor of this perspective, which is also called named axes. And I thought it would be good to just sort of recap from first principles what kind of operations we would typically do on arrays and array programming. I'm not going to be too formal with anything, and parts of it might be quite simple, but I hope the perspective I offer is a novel to some people. And then I'll describe the sort of paradigm, the different paradigm that rainbow arrays represent. this named axis business represents. So start with the introduction, basic theory of how you can manipulate multidimensional high arity arrays, and a critique of that way of operating, which is extremely commonplace, and then rainbow arrays and what they offer. So array programming is, I guess, extremely pervasive now in our technological world. It's used in data science and visualization and machine learning and analysis of statistical data sets and that kind of thing. So I won't belabor this point, but it's just everywhere. And I suppose you could point to NumPy as being one of the sort of the biggest vehicles for these ideas about high arity arrays. It's the API that I think most people are familiar with. But they're all pretty much the same. They differ in little details of what they call certain operations, but it's largely the same ideas, just repeated with perhaps idiosyncratic quirks. And of course, I should distinguish that tensors and arrays are not the same thing. And depending on who you are, you might agree or disagree, which makes it confusing. The word tensor is now so embedded itself into the machine learning community to mean one thing that it's arguably not wrong anymore. But as we know, there's sort of tensors in physics, and I want to keep those very separate from the objects that array programming is about. So in array programming, we're thinking about regularly ordered collections of values, and how we choose to order and arrange them and how we process them is the main concern. So a lot of the kind of baggage that comes from sort of physics and linear algebra doesn't really apply to the kinds of things I want to talk about today. So in particular, the tensors the arrays that I'm going to talk about are, they're not representing maps between vector spaces explicitly. You could certainly use them for that purpose, but that's not the core point. The operations will do them often not linear. And what's really, I think, the key distinction is that the axes of the arrays that come up in practical applications with array programming are often completely different, and there's no meaningful way that you could rotate between them or create a metric that can allow you to low arrays, indices, that kind of thing. I'm going to use the word array rather than hypermatrix, and that's just because it's shorter and I'm going to say it a lot. So when I say array, I think you can replace hypermatrix to maintain consistency with the rest of the workshop, but that's just my choice in this talk. Okay, so obviously everyone knows all this stuff, but it's good to, I suppose, recap it and to define some little choices I'm going to make with respect to notation. So we're going to use the word arity for the number of axes. I hope I don't need to explain that axis here is just kind of the number of independent, I guess, dimensions. That's a very overloaded word. But the way I'm going to write them, if I write them down literally rather than with a picture, is with these nested brackets, and I'll get into that in a moment. I'm also going to distinguish a sort of key space from a value space, and I'll get into what that means. The value space here is just the space from which the elements or the cells in the array are taken. So it could be the reals or booleans or whatever, just as a type. How does this whole nested list business work? Well, this happens to reflect the Mathematica convention. I'm sure Python, the same thing, C, the same thing. You don't have to use this convention, but it seems to be extremely common. And that is that deeper and deeper levels of nesting correspond to higher ordered axes. So the list of axes is sort of conceptually describing these nested dimensions of your array. I'm going to use color often to make it easy to pick out which brackets refer to which axes of the array. And like a nice little warm-up, I think, which works for a lot of explaining this to people who are new to array programming, is to think about images, because they're pervasive in the modern world with smartphones and everything and the web. And obviously, to describe an image to represent it as data, as an array, we need three axes. So we need the x-axis, where is a pixel, the y-axis, where is the pixel vertically, and then because we can describe a color image, which is represented as a sort of a mixture of these three different intensities of light at different colors, we're going to need a color channel. So there'll be these three subpixels that together make up a colored pixel. And that's the third axis of the three array that describes an image. Now, that's conceptually what's going on, but in all modern array programming, the array axes are ordered. They're not named. So we can keep the name in the background in our heads, but we nevertheless have to pick an order to actually work with these on an actual machine. There happen to be two common conventions for how you should lay out these axes in a linear order. One is first vertical, then horizontal, then color channel. The other is first color channel, then vertical, then horizontal. And this really doesn't make a difference. We don't care about this as sort of like human users of machine tools, or as reasoning about image processing, whatever. It's a detail that might have some implications for performance or converting between image formats, but it's a distinction without a difference. And that's one of the problems with classical array programming, is it doesn't allow you to elide that difference when it would be convenient to. So to get it out the way, I'm going to introduce my particular flavor of terminology. So that's the whole array. This is obviously a matrix. That's a cell, kind of by analogy with Excel. These are going to be the axes. That's the first axis. Rows are always going to be first axis. Columns are going to be second axis. And we're going to denote the cell with this sort of square bracket notation. So that's the first row and the fourth column. And the value is sort of in the cell, right? And this object here, this 1,4, this tuple, is going to be something I call a key. So you can really see the whole array as being a key value mapping between the key space, which is the set of keys that apply to a particular shape of array, and then the value space, which in this case is whatever, natural numbers or integers or what have you. I'm also going to talk about a component of the key as being a part. So just as the keys have a key space, a set of possible keys for a given shape, the parts themselves have a part space, and these are all rectangular arrays of different kinds. So the key space is going to be the Cartesian product of all the corresponding part spaces for each axis. So that's just a summary of all that terminology. Array is a collection of cells. Cells are sort of these slots of values. The slots are kind of located with a key, and they fill with a value. The key is itself got substructure, and those are these parts. And the kind of data structure of the key is a tuple. Okay, so it's extremely common, almost ubiquitous, that these part spaces are sets of integers starting at 1, or 0 if you use zero indexing, but we'll use 1 for now. It doesn't have to be the case, but that's the convention. Now, it's often actually not needed. You could use an arbitrary set, and for color channel, for example, that's a good example of where 1, 2, 3 is less clear than RGB. Like that's conceptually actually what we're working with. We should be naming those available values that the part can take, that the color channel axis part can take. But in practice, everyone uses consecutive integers for like technical reasons. And so that's what the convention we're going to adopt here. We're going to use this little syntax for describing the key space, which is going to be angle brackets, and it really just refers to a Cartesian product of 1 dot dot n for all of the given n's, or 1 dot dot si or whatever. So for example, 3x2 matrix has got a shape of angle brackets 3, 2, which just means the Cartesian product of 1 dot dot 3 and 1 dot dot 2, and it's all these tuples, 6 tuples. Obviously, special case that's super important is that the scalar array, or a scalar array, has a shape that's empty. It's a singleton set that contains just an empty tuple. And that's because there are no parts. It's just the one thing. Now, a very, very useful way to think about arrays, which at least in computer science is like not very common, is to see them as functions from a key space to a value space. And in a way that should be obvious, because we have this concept in computer science of a lookup table, and it's just like a pre-computed function, right? And that's what an array is. It's some pre-computed function that's stored densely somehow. So really, when we do array algebra, we're just manipulating these lookup tables in various ways. What's nice about this is like a lot of things flow out from this when you adopt this perspective. For example, an array of arity n, is just a function of n variables or n inputs. Or equivalently, it's a unary function of a tuple with n components. And the trick that rainbow arrays do is to replace this tuple with a record. But I'll get to that later. So let's just like cover some basic examples just to make it really clear. We've got a vector, we've got a matrix. You can see that I'm color coding things so that the corresponding axes are, share the same colors. So the red bracket here and the 2 here, that 2 indicates that within this outer list, you have 2 components, 2 elements. And the first element is itself a list, and that is of length 3, blue. The first component of the first component of this nested list is a 9, and indeed it is, and so on. And so it's all very regular and uniform, and that's the kind of common, I guess, idiom that programming languages use for representing high arity arrays, is just as a sort of form of nested list. Okay, what are the operations what are we going to do with our arrays? And you could call this array algebra. I don't know, I've heard that term very often, but it seems like a fitting term to use. Well, to even define these operations, whether they involve transforming one array or combining multiple arrays, it's useful to have a sort of uniform way of defining it. And the obvious way is to what I call cell-wise definitions, which is sort of way of working backwards. So we've got a bunch of sort of input arrays that we want to combine somehow, and we're going to produce an output array. And the most flexible way of defining things is just to work backwards, to define what a cell of the output array is in terms of the cells of the input arrays. And a core part of that is how the parts of that cell will flow into the parts of the input cells that you're using to derive that output cell. But of course, although this is very flexible, there are like some underlying recognizable primitive operations that we can encapsulate and give names. And of course, like you look at NumPy or whatever, and that's actually what you do. You can write this kind of definition with things like einop or einsum, but for the most part, you are just plugging together these primitive operations to build the computations you want. So I'm going to adopt my colorful notation right from the beginning. And this is not rainbow arrays yet, but it's going to sort of hint at it. And the way I'm going to do that is to drop explicit symbolic indices. So these are the parts of the key that are being used to look up a cell in the array P. And instead just use little colored circles, because really it doesn't matter what you name them. The important thing is to see how they match up in an expression. And so color is like a lovely channel of information to do that visually, that symbols are harder to pass, harder to match. Colors are very clear. You can just instantly grok where the colors are in common. But crucially, this is just a visual aid, so it's not semantically meaningful. What really matters is the order of these parts, these arguments that I'm passing to the array P as a video function, right? It's the argument order that matters, not the color. The color is just to help you, the reader. Okay, so I suppose you can just partition. This is like, there's more things you can do. There's obviously like weird things like convolutions and blocked maps and this kind of thing. I'm not going to go into all of those details. You can certainly set them up in a framework like this, in a conceptual framework like this, but I'm going to focus on sort of core operations that are really the meat of what array programming is about. And you can split them into the unary ones that just take an existing array and transform it without any other arrays being involved, or n-ary or binary operations that combine multiple arrays. And typically they can change the number of axes. So let's get into it. Like, what are the unary ones? Well, the workhorse, I suppose, one of the workhorses is broadcasting, and that takes you up the arity ladder. Sorry, I have a missing image here, but we'll have some examples. So the way that works is you take a cell of your array and you somehow smear it across additional axes that weren't present in the input array. So for example, if you have a scalar, you can smear it some number of times to create a vector. Or if you have a vector, you can smear it row-wise or column-wise to create a matrix. And the crucial point is really just how you're feeding, in the cell-wise definition, how you're feeding these parts of your key into the corresponding keys of the original array. What's a good notation for this? Well, let's use superscript notation. The convention we're going to use is that there's an index where we're going to insert a new axis in the original ordered list of axes of the input array. And then there's a size that we're going to pick, like how much smearing do we want to do. So for example, starting with a vector, we can smear along a fictitious novel second axis that doesn't exist in the input, and we'll get this sort of like repeating rows, or we can smear along the first axis and get repeating columns. And this is like applies arbitrarily. You can do multiple such broadcasts at once. So you could turn a scalar into a matrix. And from the function perspective, what you're really doing is providing a view of an original matrix where you're just ignoring one of the parts of the key. So you've got an additional key, an additional part of your key that simply doesn't play any role, it doesn't affect the value, and that's why the resulting array is constant along that axis, and it simply doesn't matter. So another like somewhat tedious but super important operation would be transposition, which you could call axis yoga. Obviously the most familiar one is just transposing a matrix, but a good example that references back to the case of images is changing the convention of images from XY color channel to color channel XY. And the way, obviously, to set this up is to just define a permutation on the integers involved in your list of axes, and your transposed array will just present the original axes, but it'll kind of switch around the parts of the key, so that the result is the same underlying values, but presented in a different axis order. So I suppose where things get more computationally non-trivial is with aggregation. And I actually shouldn't even say monoid here. It doesn't have to be a monoid, but any commutative operation. So if you're working with your value space as a field or a semi-ring, there's just like plenty of things to choose from, whether it's sum or mean or product or and or Boolean values. You get the idea. And the core point here is that you can delete an axis. So you can present a view of an array in which one of the parts, one of the axes is not present. And the way that it works cell-wise is that if you're going to look up the part red-blue, the cell corresponding to key red-blue of a 3 array F, you will just hold red and blue constant and then take the sum of all the possible values of the green part. And that's very uniform, and it applies to any operation. It's not somehow specific to summation or anything. Like a slightly more mind-bending one is folding. And the core sort of, the example of that is taking a matrix and decomposing it into its row vectors or its column vectors. So here's our matrix. We can see that as a vector of vectors. And what does that really mean? Well, recall that you can see with this function perspective, you can see any array as a map from a key space to a value space. And the value space might itself be the space of functions from a key space to a value space. So it might itself be an array. And so we can see a matrix as a vector of vectors in two different ways, depending on which of the two axes we're going to pull out in this sort of folding operation. And in computer science, this is often called currying if you just see it as a function. So the core observation here is like, once you've picked the axis that you're going to kind of hide, you've got something which has one fewer axes, and when you ask for value of one of its cells, you will get back another object that is itself a vector that's now ready to accept the path that you hid. And when you do that, you've now got the value of the original cell in the original array. You can do multiple of these foldings at once, and that'll give you an array whose values are not just vectors, but arbitrary arrays. Here's just an illustration of getting row vectors or column vectors. It's fairly straightforward. Okay, so those are the unary operations. What are the binary and arbitrary arity operations that you can use to combine array two or more arrays? Well, if you have any operation on your value space, you can lift it to operation on your arrays themselves. Sort of goes without saying. In fact, I've somehow messed up this example. That should be a plus over there. Sorry about that. But yeah, that shouldn't require any further chatter from me. Okay, let's put some of these things together. So let's do sort of tensor product of two vectors. So nice way to do this sort of purely algebraically in terms of broadcasting is we know what tensor product of two vectors is going to look like just definitionally, cell-wise. We can leave a little gap here, and that's going to be a broadcasted version. So this is a vector, but we can broadcast it up to a matrix. And that too just means we're dropping this component. So like this part of the key. So it's the same thing, doesn't make any difference. But now that we've got two matrices that share the same axes, we are ready to do an element-wise, we can do an element-wise multiplication. So we can re-express this as a operation on arrays. And now that we've got these sort of identity, cell-wise identity, we can conclude that vector tensor product is just this broadcasting plus element-wise operation. Another example along these lines is matrix multiplication. So here we've got broadcasting plus element-wise plus aggregation. So first we're going to broadcast up the matrices that we want to multiply to 3 arrays. And they'll each have the missing axis of the other that comes from the other array, right? Once we've done that, we can do an element-wise multiplication and then do a summation. Or at least we can re-express the summation we were keeping in the back. We can now just interpret it as a array summation, an aggregation operation on the entire array. And so that's how you express matrix multiplication this way. Okay, final thing that's a bit weird, that's not like that familiar, would be picking. So picking is when you can use an array of positions, so of keys, to pick the cells in another array. So in other words, the value space of the picking array is itself the key space of the array that you're picking from. So that's what this sort of like suggestive layout of these types is for. And unsurprisingly, that's just the ordinary function composition of these arrays as functions, right? You're just chaining them together. Now, here's some simple examples. You've got a scalar picking array, using that to pick from a vector. It just picks out the second component. But you can have a picking array that's like a matrix, and you'll get a matrix of lookups, not a single one. You can similarly pick into an object that's an arbitrary array. And like all of the weird gather operations that you'll see in NumPy and Torch and whatever are just various named variants of this core idea that strangely haven't been unified into like one thing, often, at least the last time I checked. Okay, so what's a critique of this? It all seems quite straightforward. What's wrong with this? Well, as I suggested earlier, the main problem is that these keys are tuples. So we locate keys with a tuple of parts. Tuples are ordered lists. That's a data structure. Is that a good choice for identifying or locating cells of arrays? And well, why is it this way? I suppose you can trace the different ways it might have changed at some point, but it didn't. At least in the world of array programming, it's the de facto standard. And I think there's several reasons for that, but the main one is probably that it's very friendly to machines. So arrays must be laid out in consecutive positions in memory, and it's very easy to do that, and it's well defined how to do that if you have an ordering of axes, because you can compute strides and you can calculate exactly where each cell is going to go in memory. Another way of saying that is that it's very easy to compile an arbitrary array into just a giant vector. There's a unique way of doing it. Okay, why are they not a good choice? Well, if you actually look at like a implementation of some deep learning technique like transformers, you will see endless repetition of comments that are documenting what various tensors shapes are, different points in the program. So those comments will say, first axis, that's batch dimension. Second axis, that's the kind of component of the query vector. Third dimension is going to be the component of the sequence. And it's very easy for those comments to be wrong. It's also very easy to make mistakes, to like have to use trial and error to figure out whether what you're doing is the correct thing or not. And sometimes it can seem to be correct because things just work and the program doesn't crash, but it's completely not doing what you thought, and the dimensions just happen to match, and so you got a result. And also to like get things to do the right thing, you've got these sort of basic operations, you've got, whatever BLAS operations available to you, or the primitives that NumPy provides, or PyTorch, or what have you, and you have to coerce and contort your arrays into the right shape, right axis order to do the right thing. And that can be extremely tedious and error prone. And it just doesn't feel like the kind of thing that humans should be doing in the modern era. So I'm not the first person to have noticed this. And in fact, people have worked on this, and there are libraries that let you solve this problem. But I want to make a little historical kind of analog of this, which goes back to the early days of computer programming. And it was, people were writing programs in the form of assembly code. They were manually storing data in different registers in a CPU and having to keep track of like register number 3 is what is now containing the temperature of the rocket engine, and register number 4 is the time since launch. And then like you call a subroutine, and in the subroutine something else is going on. The registers are allocated differently. So this is like constant juggling of numeric indices, numerically labeled slots, and the sort of semantic qualities and quantities that are relevant to you as a practitioner is extremely error prone, tedious, just horrible. And it took a surprisingly long time for people to just realize, we should have high-level programming languages where names are the norm. And it's up to the compiler to figure out how to allocate those optimally to the underlying registers. It really shouldn't be part of what programming is for 99% of people. And that's, I think, where we are at the stage with array programming. There's just like this mismatch between how human beings think and how these libraries work. And for whatever reason, our thinking about arrays, at least mathematically, has that same feature, that it's oriented around tuples and around ordered lists of dimensions or axes or whatever you want to call them. So what are rainbow arrays? Okay, so the solution is to replace tuples with records. What's a record? Well, it's a comp sci term. It's like a named tuple. It's a tuple where the fields are not ordered, they're just named. And those components are no longer the first, the second, the third component. They are the 8th component, the bth component, the cth component. Order doesn't matter. I could write that in a different order. It would represent the same record. So what happens when you do this? Like everything I've discussed before with this conceptual framework stays the same. The difference is that axes now, instead of being ordered, become named, unsurprisingly, because the keys are now records rather than tuples. And shapes also become unordered and become named. So instead of this angle bracket 324, we will now have, the 8th axis has size 3, the bth axis has size 2, the cth axis has size 4. And it just corresponds to the same set constructor notation, but this time we're making records rather than tuples. So my little quirky take on it is, these records seem to introduce a lot of extra noise. Now you've got these A's and B's and C's floating around. Well, you can sort of have a an imaginary legend on the side of your workspace that's like allows you to identify colors with these names. So we're going to drop the names, just use colors from now on. So these colors now give us a way to write records that looks very similar to tuples. So this 5 through 2 is no longer a tuple, it's actually a record. The way you can tell is obviously the colors, but also there are no commas. So that's how and the lack of commas, again, meant to denote that there's literally no order to this. Shapes come along for the ride. So this shape 3-4 is the same as this shape 4-3 because it's the colors that are meaningful. Notationally, looking up cells of arrays, you replace just like we did with the tuples, we replace the sort of comma notation with these colored circles again, but now no commas, they're all smashed together, and again, order doesn't matter. But important to keep in mind that underneath that is shorthand for a full record lookup. So A is a function that takes a record, the record looks like this, and these are sort of meta-syntactic variables. They're like symbolic IJK things that can take on any value that's meaningful in that case. Okay, and again, to indicate the type of an array, if we don't care about the value space, we just care about like what's the shape of the really primary thing is what are the colors that are present on an array. That's the thing you have to know in order to like define the semantics of array operations. And for that, we'll use this little fragment of function signature syntax. Let's look at an example to make it really concrete. Image, 4x6 image, 3 color channels. In the tuple formalism, the shape of this image would be 463 under a particular convention of layout, of axis layout. In the record formalism, there's no conventions necessary. It's just well-defined. This says y equals 4, x equals 6, c equals 3. And then a particular subpixel that I've highlighted, like a particular cell on this 3 array, would have, in the tuple formalism, the key 2, second row, 6th column, the R channel, and the corresponding record is much more explicit and clear. It's y equals 2, x equals 6, color channel equals 1. You don't have to figure out what that means in a particular context. So how does this change the other parts of the API, right? The array algebra. Well, transposition goes away. You can't transpose something that doesn't have an order. But there's a corresponding concept, much less necessary, although still maybe necessary, of recoloring. Aggregation is the same, folding is the same. Interestingly, broadcasting becomes unnecessary because element-wise operations automatically broadcast over the missing colors that are present when you combine several arrays. So not only do we get rid of like 2 of the nasty operations that plague a lot of practical work of transposition and broadcasting, we also gain the semantic clarity. It's like just part of the type of an array, like what it means or what the axes mean, because that's what the colors mean. So I won't belabor this, but in recoloring, we replace a permutation with just a function on colors that says how to translate the keys of the recolored array back into the keys that are needed for the original array that we were trying to recolor. So for example, we had a red-green matrix, and we want to turn that into a red-blue matrix. Well, we can do that by renaming the blue field of a key record to be green. And that allows us to plug that key into the original matrix and get the corresponding cell value. So that's the kind of long-winded way of saying that. Interestingly, you can also see recoloring as picking, but I won't go into that. So as I mentioned, element-wise operations become the only thing you really need. They're just automatic broadcasting means that they just do the right thing. There's a unique way of taking the element-wise combinations of any number of arrays as soon as you have colored axes. Let's look at how that works. So here we got a vector times a vector. No, it really, unlike before, it depends what the colors are. So before we just had like, a vector is a vector is a vector, but now we have colored vectors. It matters if you multiply 2 red vectors or a red vector and a green vector. So let's look at how that works. So here we have two red vectors. There's only one thing that it can mean, which is you multiply them literally cell-wise. Let's multiply a vector and a scalar. So scalars have no color. So there's no possible way that you can do anything other than multiply the single cell in the scalar with any given cell of the vector to produce the cell of the output. Now let's look at a red vector multiplied by a green vector. So again, like you have no choice in how you define the cell-wise definition. It's just like you just take all of the type of the product or the combination is just the union of the colors of all of the input arrays, and then you just take those parts and you plug them into each array in the expression, and you plug in the available colors that array can take, and that's all you can do. So it's completely unique. There's no subscripts or decorations necessary to like have the data flow in the right way. It's just there's only one way to do it. So in this particular example, we are computing I think this is a tensor product. Yeah. Now notice that on the right-hand side here, I could have written this in two ways. So because the order of nesting doesn't actually matter, I have a complete freedom of how I want to write it. I just happen to write it this way. It's the coloring that matters rather than the ordering. So now let's look at matrix times matrix. There are going to be three cases depending on how many shared colors there are. So there's like little combinatorics to this. If we have two shared colors, you get Hadamard multiplication. If there's one shared color, you get half of a matrix multiplication. So you get a 3 array that's just waiting to have the shared color summed to produce matrix multiplication. If there are no shared colors, we've got a red-green matrix and a blue-purple matrix, then you get, I suppose, tensor product again. Actually, no, wait. I think this is called Kronecker product. Sorry, there's like a zoo of these things, and it's like there's no nice uniform way of describing them. So apologies if I sometimes get them mixed.
I feel like when people say Kronecker product, sorry to interrupt, I feel like when they say Kronecker product of matrices, they mean the matrix that you get from a particular unfolding of the tensor that you wrote down in the last slide. There's some ambiguity of which matrix you should write down, but anyway, the one that the Kronecker product gives is the one where the determinant of M times the determinant of N is the determinant of the big matrix.
Got it, thanks. Okay, so yeah, as I mentioned before, with one shared color, you're on the road to defining ordinary matrix multiplication. All you got to do is sum that color away. And unlike before, where we had to use a subscript to like denote what axis we want to aggregate, here we would use a color. So you can just color the operation that you're doing the aggregation over. So I should correct this, I suppose. Okay, so a lot of talk. What's a really simple example? I'm running out of time, and I anticipated it would take long enough that I wouldn't be able to go through a really deep learning example, because it would just be as much of a struggle to explain what's supposed to be happening as it would be to explain how rainbow arrays make it better. But this is hopefully going to give you a flavor of like why this approach is, I think, much clearer. So here we've got an image array that represents an image. So it's got X and Y and color channel, and color channel is the purple axis. Then we've got a tinting factor. It's like we want to change the color balance of this image. We want to make it less blue. So blue, in this case, is the third part, the third, I don't want to say, third component of that axis, right? By convention. So if we want to apply that tinting, we've just got this vector that represents how much of red, green, and blue we want to achieve. And unlike with the traditional way of doing things, you can just take this thing that's like, it's manifestly a color associated array. It's like an array that's a vector that's talking about red, green, and blue. It's talking about color, because that's what purple means. And it is an ordinary element-wise multiplication with the original image array. There's only one thing that can mean, and it does the right thing. So it just multiplies each of the color channels with the corresponding factor, and the other axes are just preserved unchanged. There's nothing happens to them. A similar thing happens with, and that's actually like a nice feature. Like you write a program that's going to use this sort of rainbow type or named axis type of description, and it will automatically lift to any arbitrary other axes that are relevant, like batch. Very common in deep learning is you can apply a whole bunch of examples to the same network, because with training, you need to train it in many batches. So you might have 64 images that are all going through the same convolutional network. And that batch dimension is like really just not part of what the network is doing. It's just a side detail. You just lift the whole operation up one level. And like people go through enormous pains to like track that, to figure out the right ways of doing that efficiently. Sometimes you've got to shift it over by one because sequences come in and the sequence has a certain masking, has certain properties. It's just like a pain. And in this conception, like that's just not relevant, because batch would be a separate semantic dimension that just lives completely outside of what your data flow of your network or whatever is doing. And so if you input an array that has that extra axis, nothing will change. All the element-wise operations will ignore it. They will effectively thread over that axis, and you get an array of results instead of a single result by the time you get to the end. Okay, so the other operations I mentioned before stay largely the same, with that little detail that anywhere you saw a numeric index before and referencing an axis, it becomes a color. That's it. Very simple. But I hope it gives a little bit of a flavor that this idea of like keeping track of the semantic properties of the axes, giving them colors rather than packing them in a tuple where order is like somehow fundamentally important, offers a lot of clarity, quality of life improvements. You don't need as many operations, at least the number of fundamental operations that seem to be important decreases. Also, there's a sort of like compositional side of this, from a pure mathematics point of view, like what is the categorical foundation of all of this stuff? That's not yet clear. Might be quite interesting to develop. And this is the future. So this is what everyone will be doing in 5 or 10 years, as soon as they've unlearned all their bad habits of linearly ordered axes. So I hope that was useful to you guys. I hope that at least some of what I talked about was unknown. And maybe I'll just mention 1 or 2 future directions. So there's like a diagrammatic way of thinking about the flow of parts of keys as you do these various operations, as you compose things, that I didn't look at here. It was sort of implicit in all of the equations that I wrote, but it's interesting to keep track of it. And I think that's a core part of the categorical way of understanding this. So for example, taking the diagonal of an array, when that means anything, is the copying of a particular flow of a part of a key. Broadcasting is deleting a part of a key. And the circuit way of looking at that might be quite a fruitful way of going further. It'd be nice if there was a software library that like did all of this natively and allowed you to talk about colors and that kind of thing. For Mathematica, I mean, as I mentioned, they exist in other frameworks, but and there's a connection to hypergraph rewriting that I haven't really talked about and is very relevant to at least some of the people in this workshop. And as a flavor of where that comes from, the adjacency arrays of hypergraphs are obviously just like adjacency matrices go with graphs, adjacency arrays of higher arity go with hypergraphs. And so there's the combinatorics of that, and there's how to operationalize that, what they represent. Just like diagonalizing adjacency matrices or Kirchhoff matrices or whatever is like really useful for understanding networks. Like the corresponding meaning of that for hypernetworks, hypergraphs is super interesting, and it is something that I don't know enough about, and maybe there's maybe we'll hear a little bit more about that. So here's some references. There's, and this is again mostly from the point of view of practitioners in deep learning and data science. There was a very influential blog post or series of blog posts that Alexander Rush at Harvard came out with a couple of years ago that made this case. Like a lot of us had been thinking it on the sidelines, but we hadn't like really articulated why we were so unhappy with the current way of doing things. And I think he did an amazing job of making it really clear and arguing vocally for there being something fundamentally broken with the way people were working with arrays and array programming. And there's a nice kind of follow-up to that, which is this paper named Tensor Notation, which advocates like an actual human language-ish program. What's the right way of saying? Advocates a way of updating the way people write papers to like make it really clear using notations very similar to the colored notation I propose. It just doesn't have colors, it's got names, right? And hopefully that'll slowly start to make its way into the world of machine learning and data science, but people are also very stuck in their ways sometimes. And then there's a paper that Carlos and I and Xerxes put on the archive a while back, which goes into, I mean, most of what's in this talk is actually in that paper as well, but maybe without as much of the color tinting as I gave here. Does anyone have, well, maybe I should leave it there and allow Carlos to be the MC.
Yeah, so well, thank you very much, Tali. I'll try to give you a round of virtual applause, although that's always a bit awkward on Zoom, but I'll still try, because it's a very nice talk to have in the beginning, in fact. I mean, I loved how it was. So let's go back to gallery view. So yeah, it's very nice to have this introduction. I'm very glad to see the themes that we've been working on for some time, and you know, in this very clear way. So yes, I want to open up to questions just for logistics for people to be aware. We are running about 10-15 minutes over the schedule. As it was foreseen, we are going to run a bit late, so conversations can more or less proceed naturally. In fact, the next speaker is Edina, and he's still not online, so until he shows up, we can certainly comment. So please, any questions, comments? I have a few, but yeah, anyone go ahead and ask Tali. If no one wants to go first, I might just go. Luke, I don't know if you just unmuted yourself.
Yeah, I'm happy to go first. Thank you for the presentation. I have to comment. I have two different advisors, one as a PhD student and one as a postdoc mentor, and they both have different views on tensors, one in coordinates and one not. And I like the talk today because it kind of advocates for something that's sort of halfway in between, sort of treating the different modes or arities of the tensor in a uniform way, which is super nice. And I think there's something to be gained from all three perspectives, actually, but it gives a way to like talk about it. And as an example, the programming language I use most often is Macaulay 2. Everything in Macaulay 2 is a hash table underneath the hood. And if you're programming over a hash table, you can have parallelism is already built in. So if you do like a function, like, I don't know, I want to check if everything in the list belongs to some other list or something else. If the function I'm implementing doesn't depend on the outputs for each input, right? I mean, I run the thing over 1,000,000 times, but none of the outputs depend on each other. Then I should just let the program I'm working in, the language I'm working in, do the multi-threading and parallelism itself. And the language you were talking about allows for that. And I've been with the student of mine, we were able to like classify a set of tensors into orbits where there's 1,000,000 points in the space, but like every naive way of programming this doesn't work. But like if you just do map functions over arrays, then it works in 10, 20 seconds or a minute or something, which is really nice. So anyway, thanks. Those are my comments.
Thanks. Interesting. Is Macaulay, just out of curiosity, what is the origin of the name Macaulay?
There was a mathematician back in the early 1900s named Macaulay. Some much more contemporary mathematicians had an initial program they called Macaulay, which they used to do computations for commutative algebra and algebraic geometry. And then at some point they realized they need a new version, and now they called it Macaulay 2. And it's been Macaulay 2 for about 20 or 30 years, but it'll probably always be Macaulay 2. But yeah, it's a very popular piece of software that has packages developed by contributors. Everything's open source. It's popular among algebraic geometers and commutative algebraists.
Cool, thanks.
Yeah.
Any other questions or comments? I have a couple, so I just want to give everyone the chance.
Carlos, maybe you should just proceed.
I'll go ahead.
Maybe you'll stimulate some other questions.
Sure. So, I find it very interesting that you can. So, well, first the question and the comment, maybe. So the question is, do you think we can make? So what is the role of the notational structure of the actual names? I mean, I guess at the end of the day, you have to choose some kind of. You're displaying the dots in a line, or your names go in a certain structure in some way, some data structure. So my question is about how do you contend, because mathematically I can imagine that all I'm thinking for the keys is some kind of set, or maybe multi-set or something like that just carries the assignment of the record, right? Is that a correct way to think of the keys?
So if the keys are tuples, which is the classical thing, then I suppose they're just tuples, right? But I mean, like, they're never really often instantiated. So they're just a conceptual gadget to understand what the array is doing, I suppose.
Yeah. So, for example, so more concretely, how would you? So I imagine. Sorry, I mean the names are going to be a bit mixed. So you're calling it. So what is the name for an index again? I want to use your terminology in this, at least in this section.
Depends what you mean by index. But so if to identify a single cell, right?
Yeah.
AKA value in an array, you need a
key.
A data structure. You need a key.
Right.
So the key is going to be a tuple, and the components of that key are going to be, I call them parts, but you could call them indices.
Right. No, because I just. So maybe this is the change in perspective, and that's why I have the question. But I mean, typically, especially coming from the paper that we wrote together about a year ago on this array algebra, we had these indices where sets were just finite sets in our case.
Yeah.
And so you were taking. I mean, we use this structure to just say, well, we just take Cartesian products of these sets, and those are keys in this sense, and we're taking maps over this. Cartesian products into some value space, and you do this sort of monoidal category like structure, and that's where you end up with these arrays. But one of the reasons you have to do that technically, or at least I saw the necessity to do that technically, was that we wanted things like repeated indices, and by repeated I mean I wanted to take one index set, some finite set of labels, and then do it twice, right? So do that squared and so on. So I guess that's recovered. Like that's what I'm getting at. So how would you describe?
Yeah.
Like
So that's the I think I understand. So it's like that's the distinction between there's two things that could characterize a key. So you could focus just on the colors, right, and say this record has got an X, a Y, and a C field in it. And you could call X red and Y green and C blue, whatever. But then it's also relevant, like what the part spaces are that the entries corresponding to those fields are drawn from. Mm-hmm. So if it's 100 by 100 image, right, with three color channels, then it's like that 100 is really important.
Sure.
And that's the index set that we talked about in the paper, right?
Yeah.
But then, so you're not only like taking those index sets, you also assigning them a name for the purposes of a particular array, which
Okay,
is,
I
I
see
suppose,
what
the
you mean.
color.
I see what you mean.
So you're allowed to recolor only if you're recoloring the same thing. So you're
Okay,
only allowed
okay.
to recolor the same index
I
set.
understand. I understand. Yeah.
Wow.
Yeah.
And that's like, yeah, similarly, like taking a diagonal is not well defined unless the two axes that you want to diagonalize over
Yeah.
are the same index set, because otherwise it's like, how do you match them up? That's not well defined.
Yes. 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 No. 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 I see. I see. So then, just to be sure that I understood, then the fact that you can visually with the color coding that you used, that you can visually distinguish them. It's what we normally use with like our commas or something like that. That we put sort of or juxtapose names for the indices. The fact that they are distinct in this framework will show up as having different colors. In like you would never have something like two reds together, right? Like two red dots just sitting together.
No, but there could be a red dot and an orange dot that are drawn from the same
From the
index
same
set.
index set. Yes, 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 yes. That's what I mean. But in terms of the coloring, they will never be the same. Yeah, exactly. Okay, I get it.
Exactly, yeah.
Thanks.
Hmm.
Right, more questions, comments.
How would you deal with, say, skew symmetric or symmetric
Yeah.
arrays, partial symmetries, that sort of thing? So, like a symmetric matrix only needs, n choose two, n plus one choose two entries for an n by n matrix. So you could like it's a sparse array, which not super sparse, but it's sparse, right? So your key values, you only need like roughly half of them.
I think there's an interesting answer to that. So it's something I haven't thought about terribly much. But there is an interesting thing to say, I think, which is that as soon as you adopt the perspective that key space is something you can play with, right? Like we went from tuples to records, and ultimately you can compile one in terms of the other, but like it brings out it clarifies a lot of operations. Some operations evaporate when you do that. They're not necessary. And it's more useful to human beings. But you could also have data structures that are like ordered sets. So if you had an ordered set of two elements, you simply cannot express the redundancy that a symmetric array contains, right? Because you cannot have 3, 1 as being a different key from 1, 3. They're the same key because it's now, you're not dealing with tuples, now you're dealing with ordered sets, or just, yeah, ordered tuples, for example. Sorry, I shouldn't have said ordered sets. But like you can do that kind of trick. And in fact, it becomes really interesting to imagine like what are there other kinds of bizarre symmetries that were hitherto unexplored because we were missing like an analogy or we were missing a suitable. Here's a good example, right? If the keys are not tuples but circular lists, right? That's already a kind of weird symmetry because it says that IJK and JIK, or I don't know, whatever, they're all the same, they're the same key. And that's like a property of the data structure. It's not some kind of symmetry you impose on a particular representation. It's just inherent. So that's a very computer science-y way of constructing a symmetrized, and like you can have representations of it in terms of actual ordinary arrays, but so like I like that way of thinking, but I really haven't explored it very much.
I make a suggestion with the notation and names that you used already. Like you could have a function on key space that modifies, like gives you a way to find the values for keys that don't exist. So if you have only ordered lists and you don't require key space to be rectangular, you could just have whatever set of keys you want. Then you could have the function that says, ij to ji with no penalty, just copy. The function's called copy. It copies the value. You could also have like negative copy as the function. So if you switch ij and ji, you could tell it to give you the negative value that you had at position ij. And then if you have a triple of indices, you could have a function that says, if you want the circular permutation of them, copy. But you could also say, like, if I swap to negative copy.
Yeah. No, that's a nice way of rephrasing those. Yeah, exactly. I like
So then you
that.
can embed all of those discrete symmetries into that. It's a function on key space that allows you to provide the rest of the values of the imaginary rectangular array from only knowing some of the values.
Yeah, and another way that you could maybe set that up is to, and this would have to wait for categorical foundation for this stuff, but like you can have just different kinds of arrays all playing in the same sandpit, right? So you've got arrays whose keys are circular lists, arrays whose keys are whatever, ordered lists, arrays whose keys are tuples, and then define appropriate mappings between them, or have separate categories for these objects and have functors between them, right? And then you can ask about, what are the images of these things and pullbacks and all kinds of categorical gadgets to like get a hold of them. That could be quite interesting. Like I'm excited about the category theory aspect.
I could just contradict myself for one thing to use the going backwards. So if you allow the keys to be unordered, unordered lists, right? Then you don't have to store as many keys. But if you require like all the keys plus a function that tells you how to move between them or something, you don't really get much of a savings. You maybe save fewer values, but you don't have to save all the keys. So if you use a different data structure type for your keys, then you are immediately doing like the sorting or whatever. If two keys have the same sorted value, then you don't actually have to build a bigger structure. So that might actually be more of a savings than I don't know how to do like the skew symmetry that way, but
so
right. I mean, if you like a 9 by 9 by 9 by 9 like 9 times array, you don't want to store all the keys, much less the values. So, but if you have some kind of skew symmetry, and I'm mentioning this because this is the key feature I used in Mathematica a while ago. The skew symmetric sparse array structure was super useful. No other program that I used could store it, use it, much less. But it could Mathematica.
Yeah, if I may. Yeah, sorry, Josh. I think you were about to say something.
Oh, I was just going to say, yeah, it's interesting. The skew symmetric and symmetric cases and like the cyclic case, things like that are interesting for lots of applications. But also, if you try and generalize to other symmetry classes of tensors, like living in other, I know Luke at least knows that, if you hit a vector space with a Schur functor, right, and so it's like some indices are symmetrized and some are anti-symmetrized. Then when you try and do something like this, you'll start to get into like whole rewriting rules, right, for whatever that Schur functor is. And like for symmetric and skew symmetric, those rewriting rules are very simple. But for an arbitrary symmetry class of tensors defined by a Schur functor, like the rewriting rules are quite complicated. But it's certainly interesting to think about, like for particular one, like even for the only other three-way Schur functor, which is like two variables are skew symmetric and the third one is symmetric. That corresponds to a certain class of algebra, like roughly speaking corresponds to Lie algebras. And so like you're talking about like rewriting in terms of bracket or something like that. But it's interesting to think about like how you might get that to compile down to something that has the same level of efficiency as sort of the ordinary array thing, like you were talking about, Tali, where you can predict exactly what the indices are, right? So it's super efficient.
Yeah. If I may add something here, I think it's. I mean, I love that we landed on this question because it's one of the key questions that I've been struggling with, and Nick and I have been working. I mean, just to reference what Tali mentioned at the end of future work, we've been working on hypergraph rewriting and sort of translating hypergraph data into hypermatrix data, and I must say that the most natural encoding of hypergraphs that we currently have squarely places us in this territory where we have to contend with the fact that arrays, if based on tuples, they're gonna have a lot of redundancy because, for example, we are starting to do everything with undirected hypergraphs just to begin with, the most direct analog of traditional graphs, and so it's very wasteful to just say, well, you encode all the tuples and then all the symmetries that you have, and you have a big group of symmetries of your thing. So just to give I would like to have conversations about this because, at the moment we are waiting on Edina, on our next speaker, and it's possible that he got the time wrong or something was off. But for now we can chat for a bit longer. If it takes longer, then we can see how to adapt. But otherwise, I would like to have this conversation sort of expand into a proper sort of maybe time slot at some point where we can all make it and have a sort of longer conversation, because the way I see it, and referencing what Tali's comment on the prospect of the categorical context and the categorical formalization of these things, one of the viewpoints that actually clarifies many things about the data structure of your key space, right, is that you can begin to think about automorphisms of your key space as sort of the replacement of the symmetries of the objects themselves. So the objects become sort of more unique in some sense, and then you have automorphisms, or generally morphisms and isomorphisms of your key spaces as the symmetries, which in some sense are the relevant symmetries that you want to capture. I mean, I think everyone agrees that if you reshuffle the ordered list of indices of a tensor, nothing should really change. I mean, it's just the convention that you took, and it's in that context that I think these questions are going to become relevant. But anyway, I really wanted to sort of place a marker on this topic, because to me it's one of the difficult things to address, and I like that you mentioned, Josh, when you have mixed symmetries, because that's one of the things that we are doing. I mean, we are thinking of, for example, we want to cover undirected hypergraphs, we call them tuple hypergraphs, or ordered hypergraphs, where your hyperedges are just tuples of elements. But then we also have cyclic ones, and then we have the standard definition of directed hypergraph, which is many to many, right? And in many to many, you can have, it's effectively a two-tuple of some other structures. It can be cycles to cycles, or or unordered lists to unordered lists, and things like that. So in this diversity of symmetry, it already makes sense for us to kind of have a parsimonious treatment of array symmetries. And of course, on top of that, we have the question of a hypergraph has mixed orders, so it has edges of all sizes, and then we have to take all the adjacency data on some. So just to riff on the name array and HyperMatrix, I normally tend to use array for something that I mean, as Tali described arrays, right? They have a defined dimension, so they're just an assignment from some keys into some values. And HyperMatrix for me is what comes from hypergraph. So the name hyper is sort of inherited. So when the hypergraph is mixed, then you have so you can sort the orders of arrays. So it's some kind of sorted or maybe direct sum in some way of arrays, right? So in that way we can have hypermatrix and array, and be kind of coexisting without having to be contradictory in any way. So
kind of like a power series. It's like a formal power series of
something like that.
Yeah.
And you can always imagine that all the irrelevant orders are empty, and you have only all arrays can be seen as a hypermatrix. Where with this kind of view, so we can use both, and there's no really taking sides when you use the names. So
yeah, it's a kind of graded algebra, graded by arity.
Yeah. Right. Any more questions, comments? So unfortunately, you haven't heard from Edina. Yeah, Max.
Hi. Yeah, I have a question which comes from a completely different corner, but I think is sort of curiously related. So in knowledge graphs, one of the weird things is that the data we collect is typically incomplete. And the first time when I realized that mathematicians and programmers and people who deal with large data sets typically have tuples. They basically they store a matrix without sort of like the labels on the side. What you're suggesting, Tali, is very, very similar to like what we sort of did in these databases sort of by default, like basically key everything, basically, right? And that allows you to sort of deal with matrices where you lack entries or something like that, and you still can work with that. And why do I bring this issue up is Wolfram Alpha is one of the very few areas where these two things mix, where Mathematica mixes, like all the functionality of Mathematica mixes with sort of being a knowledge graph database. And I would be curious about like in how much this sort of equivalence sort of something that is discussed, because as we collect data, we still run into this problem, like when we say, we have a large data set of all of the information about the city of Rome, for example. Then one of the key issues is we try to fill in gaps as the humanists, but at some point we also realize, oh, there is mathematical structure going on in, I don't know, the bipartite network between churches and drawings or something like that. And so there's a kind of weird moment when this sort of like more, oh, it's a table kind of thing changes into, oh, it's a matrix. And your coloring is sort of something that is actually super useful on that sort of more pedestrian table side also. And the question is in how far you can take that. How far can you take that? Having three colors is one thing, but once you have to deal with sort of like dimensions where there's lots of stuff going on, where it's sometimes not even, it's sort of curious what's a key and what's data. It's sort of like a weird thing. So is that something that is on your radar, or is that something where there's really a distinction? There's like the database part of Wolfram Alpha and there's Mathematica.
Well, I think so. It's a really interesting kind of line of thought. There is a connection between hypergraphs and databases. So like formally, hyperedges are rows in a database, at least the appropriately chosen kind of hypergraph. So it's one of the complaints about hypergraphs is that they're so general that they're universal medium for computation. You can represent anything with hypergraphs. I suppose you can ask, like, what's the point of why use hypergraphs and not some other formalism for thinking about things? And I guess what's nice about them is that they're very clean. So they're very clean, abstract, simple setup to think about how things are connected with one another. And I suppose you can rephrase all observations as conjunctions of like primitive facts. Like I was here, I saw this, and at the same time it was raining, and someone else told me about this fact, and you can link all those things together into a hyperedge. And yeah, as for I kind of trying to parse your question about like the connection between Mathematica, the formal programming language sort of system, and knowledge graph. I would make the point that I do think a lot of knowledge is currently organized in a very binary way. So like lookups are typically like, what is this property of this object? And that's true of Wolfram Alpha, but it's like true of almost everything that's out there. You don't see very many lookups that are ternary or quaternary in nature. I suppose you can, like time would be a good example. Like, what was the property of this object at this particular time? Right, that is a ternary kind of question that links an object axis, a property axis, and a time axis. But and you can ask that in Wolfram Alpha, I suppose. But like, is your question like, where does that, what does an arbitrary arity hyperedge look like in that case? Like where does it end? I'm not quite sure what.
Maybe an interesting way of putting it is the following: like, if you have something like Fortran going on and you have lists that have no gaps and start with 0 and that's it, then basically, obviously, that's the most efficient way to deal with it. But the moment you have to deal with historical data where there must have been something, but it's not there, so you color it in an interest. So you give it a key in some interesting way. And then once you have given the key, it doesn't really matter if entry 16 is missing and you only have 15 and 17, for example, right?
Yes.
And so in some sense, for somebody coming from that world, going into, say, a place like network science, where people by default worked with programs that actually had sort of like, sort of start with 0 and count and there's consecutive numbers, that is sort of something where it's like, how could they, right? Like it really takes a long while to understand, okay, they do this for computational reasons, to be efficient and store more stuff in less space. But the key thing is now, if we do this transition, and I find this very surprising, very refreshing that you suggest doing that for a different reason. But then the key question is, okay, what is the drawback? Like, can everything be done in this kind of way while still being sort of efficient? And
yes, 100%. So like, absolutely, you can compile anything that you would write in sort of colorful notation or rainbow notation into an equivalent ordered access program. And in fact, it's better because you can have automated techniques. And people aren't doing this yet, but I'm extremely confident they will do this in time. You can have automated techniques that figure out what is the best ordering of axes to maximize the coherency of memory access that will allow the caches of my GPU or my CPU to optimally, and maybe things like Fortran do actually do this kind of thing, right? But to optimally compute some very complicated high arity array expression, right? Like it can figure out that although, like if you're writing an old-fashioned program where it's like, you said that this is at axis 0, this is at axis 1, this is at axis 2, then like you locked into that commitment from the beginning. And so what the compiler can do is pretty minimal. Like it can play with loops and whatnot, but it can't confuse some operations maybe. But it can't decide that you should have computed a transposed version of that because it would be more efficient. Or if in theory it could, and maybe things do this, but then like keeping track of how to trick you into seeing what you thought was there when in fact a different computation is going on becomes like a more and more dangerous game for the compiler to do. So I don't think they're terribly successful to that. But if you just say, I have these axes, I've got time, I've got space, I've got color, or I've got temperature or whatever, and like I've got some sparse data that lives on this or dense data that lives on this, I don't care how you arrange it in memory, just like here's how to load it from disk and here's the kind of things I want to do with it. Then like there's such a large space of automatic optimization that the compiler can do to turn that into something that is linear in memory, right? And it can potentially do much better than you could ever do by hand.
Mm-hmm.
So I think like the future is this not only for human reasons, but for machine reasons. Like decoupling human beings from machines has maybe initially led to slowdowns because you can't hand optimize things, but eventually will lead to speed ups because you could never hand optimize as well as a very sophisticated compiler that has a global view of what's going on.
That's similar to the transition to the connection machine CM5, right? From earlier versions where at some point sort of like you would program a connection machine, but the hardware would actually be different. But there was this translation step in between where exactly this kind of like optimization would be done. That's a really interesting idea. Like the question is like, in how much can your work basically sink into stuff that the machine just does and nobody thinks about it, which is also dangerous for us.
Yeah.
Thank you.
Yeah, that's actually a very interesting line of thought. So before possibly delving further into that one, I wanted to offer the option here because Edina is not replying. Maybe something unexpected happened. So we have an option. So we basically have 30 minutes or 25 minutes until the next session, the scheduled time. So because both relevant speakers are here, we can do as you prefer. We can either take a break now or continue informal discussion until the time and keep on the schedule. We can shift it 30 minutes, about 30 minutes, 25 minutes early. It's up to you. The two of you are here, so as you prefer.
I think I'd prefer to keep the schedule just because, like, if people were planning around attending certain talks or things like that, yeah. But it's been a great discussion so far, so yeah.
Yeah. No, I'm glad that you said that because then I think keeping the schedule is always better because it's been advertised and people have been in different time zones. So in that case, let's continue with informal discussions and maybe 10 minutes before the time we can take a break and then reconvene. So yeah, I mean, just to put two pins on what's been said, Max, if I'm right to characterize what you've been saying, is it the case that you're pointing at to what degree our machines are encoding this data structures more or less explicitly, so that the algorithms themselves that we program on them are more or less efficient. Was that part of your line of thought?
Yeah, that is sort of like where the discussion took us.
Yeah.
So where I was coming from was this thing that there's this transition between when data is data and when it becomes a mathematical object. And if you come from the side where data is data, and particularly if you have to deal with collections of data that are incomplete or deteriorated, or like you have a shabby lens in front of your digital camera or whatever. So whenever you have to reconstruct something, it's better to have a keyed data set, for the simple reason that your matrix order may not be the right one. And I think that is, a really interesting sort of transition point. And ironically, there's a similar kind of there's similar operations possible then in this case, where you say what Natali brought up, where you actually go and you translate something into, like, you pretend the machine has one kind of topology in the GPU, whatever, but in fact there's something completely different going on, which is just too hard to sort of wrap your head around. Yeah.
I wanted to jump into this conversation too. I think another thing that Max is talking about with missing data, suppose you wanted to sample the entries of a tensor with the traditional way of like programming before, keyed data sets or whatever. For very large tensors, you wouldn't even be able to get started because you have to declare an array of zeros first and then start populating the entries, and maybe you don't even have enough memory to declare the array of zeros, right? But maybe only like 1/1,000,000% of that array actually has information in it, and the rest are just had better be empty, or maybe there's some symmetry which allows you to only record some of them. It's a different type of sparsity when there's symmetry. It's like less information than what's actually the number of pieces of data that are in the array. But I could say for like stochastic gradient descent methods for machine learning, like you could do, and I have a paper on this topic, so it's like self-advertising, I realize, but like you could try to do algorithms with matrices or tensors that don't use all of the entries of the matrix or the tensor or the array. So for instance, if you wanted to multiply two matrices, we figure we need to know all of the entries, but what if you only needed to know one entry of the product of two matrices? You can get away with a single row column product, and you don't actually need to know the rest of the entries of the original matrices. So your matrix product operation could even work when you literally don't know some of the entries of the matrix. You could still multiply some parts of the matrix. And just to add to that, you could also imagine writing a program where you put like a discrete probability distribution in front of your keys. And you say, what's a random entry of my tensor? Well, you sample from this discrete distribution that selects one of the keys, and then you take the value for that key. And it's interesting to think about algorithms that could possibly be provably like convergent to the thing you're looking for, where you never actually have to store the entire tensor. Maybe you could actually find a rank 1 decomposition of the tensor or so on, even when there's missing data or when you're just probabilistically sampling some of the entries.
There's another, maybe a sort of similar twist that you can play as soon as you kind of got this view of arrays is, yeah, not necessarily. And I think frameworks like Julia are doing a bit of this, and I saw even Pandas 2.0, which is like a data science framework, is doing a little bit of this, which is that you can have like a logical view of an array. It just seems to be an ordinary array, nothing funny going on, but it might have a complicated tree of like partially realized or efficient or customized gadgets that are being used to produce values for the given cells. So, and can handle things like missing values. So you could have a dense array that stores all the numbers that are supposed to be there. And one of the problems with missings, of course, is that like they ruin packing. Because like if you had, I don't know, floating point numbers, well, you can use nans for floating points, but if you have integers, you have to do crazy things like sentinel values that represent something isn't there. in a corresponding cell, right? A time series. Like you want the benefit of density, the memory benefit and computational benefits of density, but you also have missing values in there. So there's often no nice way of doing that. You just have to like remember that like certain values mean that something's not there, but then you add one to everything, and then suddenly the sentinel value is the wrong value. And so what the pandas people have started to do, and I assume it's being used elsewhere, is that you can maintain this like more complex compound data structure, which is a densely packed array of data, some of which is nonsense, right? Like some of it is just dummy values that don't mean anything. And then the corresponding bit mask that's got a 0 if the thing's valid and a 1 if the thing's invalid. And then that compound data structure can just keep participating in transformations and operations, and it will just like the bit mask will just live there saying which values can be trusted. And you can imagine it doing the right thing if it goes through a convolution or a smoothing process or whatever, that it can kind of mask out the right chunk of data that would have been affected by that value. So that it's like a mixed numeric algebraic way of thinking about data flows of arrays. And I think that's an extremely powerful kind of future direction for a lot of tools to use. That's similar, I suppose, to what you're saying, that you could have these like gadgets that are just like doing potentially quite complicated things, whether they're probabilistic or around missing data or around symmetries. Yeah. And again, there's an algebra of how those gadgets compose, which is there, again, it's calling for like you need real mathematical thinking to like figure that out, like compositional, maybe categorical thinking to figure out how these gadgets should like compose with each other in a formally correct way.
Yeah, and actually that reminds me of there's a, let's see, what's the part of this story? So okay, you can think of polynomials as a particular kind of symmetric tensor, right? And sort of you could think of tensors as sort of a non-commutative version of polynomials. And when you think about it that way, like in the world of polynomials, there's lots of stuff like this, where like polynomials are often represented sparsely, where like you only represent the non-zero coefficients of the monomials, which is like the non-zero entries in a tensor. But you can also talk about polynomials being represented by like an algebraic circuit, where I don't explicitly write out all the monomials and their coefficients. Rather, I give you a sequence of instructions, add, multiply, subtract, so on, that produces for you the polynomial. And you just sort of treat that as a black box. And when you want to evaluate the polynomial somewhere, you plug that into the black box. If you want to ask what the coefficient of a monomial is, you might have to unpack the black box a little bit, but like, you can still ask. But you could imagine the same thing for tensors, right? Where like you have some compact description of it, but that you still sort of have the same interface to it. Right, and this gets used in physics all the time, like when they talk about like matrix product states, like that's one particular kind of compact representation of a much larger tensor. And there was one other thing I was going to say, because you were talking about, right. A big question, even in the world of polynomials, is how to make a lot of the operations you want to do with those compact representations efficient. Is where the efficiency may or may not be the same as sort of the striped efficiency in memory that you get from like a dense tensor, say, or the source of efficiency could come elsewhere, of like, now you just treat these things as their compact descriptions and you find other ways of dealing directly with the compact descriptions. But I've mostly seen that either in the context of physics, where they do stuff like matrix product states, Tucker decomposition, things like that, or in the context of polynomials, where they do like algebraic circuits. But even there, it's like there's not a ton of work on it, and particularly not on the computational side of like, how do you actually do the things you want to do with these compact descriptions?
Yeah, can I add something at Tali before I forget there?
Yeah.
So I think those are two good examples, and in fact we can add a third example of what we are currently working on, which is exactly the goal that you described. Is that you want to think of these tensors as black boxes and somehow have a compact description and work with those. So we're currently, there's this interesting interplay or kind of weird loop that happens when you look at hypergraphs. I mean, on the one hand, you can look at hypergraphs and take the adjacency data and then make this hypermatrix arrays and so on, and then you can try and translate all kinds of questions one from the other. I mean, you take the template of conventional graph theory and the linear algebra on adjacency matrices and all the graph questions that you can deal with those. But then when you go to hypergraphs, you have this correspondence between your hypermatrix and your hypergraphs. And then what's interesting as well is that if you just look at hypermatrices or arrays in general, it's quite convenient to express, at least in some of the obvious examples of operations that we normally care about. It's very convenient to express the operations themselves as hypergraphs. Like hypergraphs have a very powerful diagrammatic function. So it's not only as mathematical subjects themselves, but once you are dealing with just arrays and maybe you never cared about hypergraphs to begin with, you're just in databases or genetic functions and so on. Like some people might care about that, or machine learning or whatever. It turns out that hypergraphs could be quite powerful at describing just the structure of some operations, because typically you would just, what you care about in these operations is typically simply the index adjacency in some sense, and incidence in some sense, right? Like you're saying over these common indices you want to do this kind of operation. These indices are sort of coexisting together but not really interacting. So this information is very efficiently captured in hypergraphs, and something that we're working on is to translate array operations directly into hypergraph operations. And for us, hypergraph operations are very generally rewriting. So it's general hypergraph rewriting, and then try to find the classes of hypergraph rewrites that actually reproduce the behavior that you encounter in array algebra. So just to give a very simple example for everyone to understand what I'm saying, when you do, for example, and calling back to some of the cases that Tali showed, if you have a graph and you think of the adjacency matrix of this graph, a simple graph, so undirected, only one edge or no edge, and simplest case, if you think of the situation of three vertices, all right. So yeah, look how to go to the class, right? See you later. So you have three vertices and you consider that you have two edges in the usual sort of path configuration. So ijk, you have an edge ij and an edge jk. You can imagine that the index incidence is that j is a common index, and so you can, for example, check that the three indices make up a ternary condition or ternary relation among the indices, that it's saying that whenever you have an edge ij and an edge jk, you have this particular topology, right? So that creates the Boolean information of a simple three graph, right? A simple ternary hypergraph, which just tracks that sort of situation. Now, if you simply forget about the information of the intermediary vertex and you say, well, if there exists at least one intermediary vertex, or maybe you want to count them if they're multigraphs, then you end up with matrix multiplication, because what you end up with is that there's a binary relation between I and k whenever there's an intermediary j between the two. So that's the kind of translation that we're doing. So it's matrix multiplication turns into this very simple checking of adjacency conditions on the hypergraph, and you can just actually rewrite the hypergraph. So you would spot that you have I, J, J, K edges, and so you would rewrite the IK edge from those, and then take the hypermatrix or the adjacency matrix of that, or you could just compute the adjacency matrix and take its square, and so you have this sort of commutative diagram, and you can do both things. So it's this kind of language that I find quite interesting to explore here, and yeah, so it's adding more sort of fuel to the fire, so to speak, in that these things probably need some kind of packaging that is compact, and think of the algebra that operates on them without going down to the level of indices or keys and their manipulations. But yeah, it's one of
the other thing I was going to mention, because Tali, you said something about like developing the math about how these sort of partially specified things or succinct descriptions compose is like, it sounds very, at least one way of doing that is to talk about something like a version of circuits for descriptions of hypermatrices. And I think, although I'm not 100% sure, I mean, the mathematicians sort of study this under the name of operads, basically, and the mathematician,
Yeah.
which Harm is going to talk about, I think, later today. There they typically ask different questions, but like the underlying object they're looking at is basically the same thing. It's like these operations that can compose in multiple ways, and you can sort of plug them into different, you know, what I would call legs of the tensor, but it's not always tensors, it's more general than that. But
Yeah.
but like I think yeah, that might be some of the relevant, you know, there might be stuff there sort of getting at what you were talking about like what's the right math for keeping track of all these things.
Yeah. So I think I agree. Operads are a good I mean, they're model expression trees, basically, of like, you know, you've got some computation flow and you're going to end up with sort of one result. And you sort of compose these trees one to the next. And you can put trees inside other trees, and it's going to represent how your data flows from a whole set of inputs to one output. And I suppose operads are just the carrier for like building algebras that can then have additional properties that you can specify, right? And I agree, they're a good match for that. Interesting.
Yeah. All right, so how about we take a break until maybe a minute before the top of the hour, and then we reconvene and we have Josh's talk. Great. So see you in a few minutes, everyone.
Okay.
Thanks to you.
Bye.
All right, welcome back, everyone. Let's resume with Joyce Bradshaw. He's going to talk about equivalences between different hypermatrix objects. I'm quite looking forward to this talk, as I've read a few of his papers, and it's a pleasure to see you in person. Well, in person, I guess, as in person as this can be, at least live. And so, yeah, please, the floor is yours.
Yeah, thanks. So thanks, Carlos, for the invitation, for organizing. I'm really happy to be able to talk to you all today. For those of you who might have missed the intros at the beginning, I'm Josh Grochow. I'm a professor of computer science and mathematics at University of Colorado Boulder. And I've been thinking about some of this higher order stuff probably for a little over a decade now. But what I want to tell you about today is some of this work that has really come to fruition kind of in the last 3 or 4 years. And so this will be based on joint work with Yoming Chao, Utorny and Sergeychuk, and also Yoming Chao and Gang Tang. And Yoming Chao, I actually want to highlight. I mean, we have several papers together, but I also just wanted to highlight, like, he also has a very interesting line of research about analogies between graphs and alternating matrix spaces, which are a certain kind of third order tensor that we'll talk about in a bit, but it's a very cool line of work, and I highly recommend it to you all. Okay, so and yes, please stop me with questions if you have them, and I'll also try and monitor the chat for people who want to just put questions in the chat. All right, so we can represent lots of things with hypermatrices. And in this talk, I'm mostly going to focus on 3D hypermatrices, partially because I can draw them and partially because we know more about them, but also partially because with Yoming Chao, one of the theorems we proved is that if you talk about tensors and when are two tensors isomorphic under change of basis, and I'll say in more detail what this means because this will be sort of a central thing, but just to, why are we focusing on 3D here? One of the things we showed is that if you go up to higher order tensors, you can actually embed those into third order tensors in a way that preserves isomorphism. And so from at least certain perspectives, it's sort of without loss of generality to look at third order tensors. That sort of roughly speaking, any phenomenon that can happen in kth order tensors can also happen in third order tensors. And this is not true for second order tensors, for matrices. Like you can't go down further than this. Okay, so just as some examples, which will play some roles in this talk, if we look at, say, cubic homogeneous polynomials, we could represent that as a third order tensor that looks something like this, where I sum over 3 indices ijk, and tijk is giving me, say, the coefficient of the monomial xi, xj, xk, right, where these are commuting variables. In, say, ODEs, if you have a polynomial system of ODEs that's quadratic, you could also represent this by a third order tensor. So I can look at something like dxi dt is, and again, now here I'm just going to sum over j and k of t sub ijk xi xj xk. Okay, and so you see, in some sense, from a pure data perspective, the same data is appearing here, right? It's a third order hypermatrix. Similarly, quantum states, I might represent this as something like this. If you look at this shouldn't say bipartite, this should say bilinear. If I look at a bilinear form, I might say things like, my bilinear form, maybe I'll write it with angle brackets. So you can think of this as like a dot product or things like that. Sum over k, t sub ijk, xk. For an algebra, right, if you think of an algebra with a binary product, you can also have a similar expression where if you have a basis consisting of the x's, you can write your multiplication like this. And then the last one, which maybe is sort of a less familiar object, but which will play a role and sort of simplifies talking about things, is what I call a matrix space. So this is a linear subspace of the space of matrices. So a single matrix space is a subspace of, say, n by m matrices. And you can represent this by giving a basis for that subspace, where you say my matrices, A1 is going to be the matrix. Maybe let me write it this way. So say I have a basis for this matrix space. Leave me some room. A1, AI, AL. And I'm going to write my ith matrix, its JK entry will just be TIJK. Right. So again, you can think of, if this is my box T, my matrix slices are sort of like this. Okay. So we have, and there are many more things, of course, that you can represent by third order hypermatrices. And again, in some sense, they're the same, but sort of obviously they're not the same, right? Like these are really different objects. So, and just to do a few examples here, so I won't do all of these, but when we talk about these things, we consider very different properties of them. So when we talk about polynomials, we might talk about things like roots or factorization, maybe things like you might look at their partial derivatives, and so on. When you talk about differential equations, you might look at solutions. For quantum states, you might look at things like, say, von Neumann entropy or partial traces. For algebras, you might look at things like compositions of algebras, so like direct sums of algebras, ideals, quotients, etc. And for matrix spaces, for those of you who haven't seen them, but like one of the things that is sort of natural to ask about if I give you a matrix space is to ask, for example, what ranks occur in my matrix space? So do all the matrices in my space, for example, are they all singular? Do they all have less than full rank? Or do they all have low rank? Or do they all have the same rank? There are lots of things you can ask about rank. So, all of these things that are represented, I mean, you could literally take the same tensor TIJK and talk about the polynomial it represents, the differential equation it represents, the quantum state it represents, and so on. But when you think about it in these different settings, which going back to Tali's talk, you could sort of think of these as different categories. We really ask about different looking things about these, right? And so there's a question though of like, okay, on the one hand, they're sort of obviously different. Like the fact that you can use the same hypermatrix to represent all of these things is it's like an abuse of notation, right? It's like, yeah, I had a box of numbers. I could interpret that box of numbers however I wanted. But we can ask sort of what is it that makes them different? Like, sure, we're looking at different things, but is there sort of one thing that we can look at that says, yeah, these are different? So one thing you could say is just, well, they live in different categories, right? That is sort of a clean way to talk about it. But to do that, you need to say, okay, what are the morphisms in those categories? And I would argue that in many cases, to understand sort of some of the key differences here, the morphisms you really want to understand are how these things transform under a change of basis. So let me continue with my list of examples here. And if it's really a change of basis, meaning that like it's invertible, then these will be isomorphisms in your category. These are not the only things that are important, but these capture a lot of sort of the differences we see. So, right, I'm going to introduce some notation. So polynomials, if I have a polynomial sum Tijk xi xj xk, okay, and I do a change of basis b to the x variables, What does that do? Well, that replaces xi with b applied to xi. It replaces xj with b applied to xj. So you end up with something which looks like sum of tijk. Maybe let me call this xi prime, j prime, xk prime, where xi prime is like the sum over b xi, right? It's some linear combination applied to xi.
Yeah.
Okay. And what I want to do is introduce a little bit of notation for this, because writing things out in indices is going to become painful. And this actually is sort of at least one mathematical counterpart to Tali's talk, where like writing things down in indices is with numbers, and I want to not be keeping track of which number is which is here, when we think of this as a tensor, it's still a 3D box. And so there are still 3 sides to it. But those 3 sides are actually all acted on the same, because they represent the same set of variables in this case. And so when you act by a change of basis, you're acting by the same change of basis in all 3 directions. And so I want to denote that by U tensor U tensor U. So U here is a vector space. And the fact that I'm using the same letter U in all 3 places says I can't do a change of basis to one direction at a time. If I do a change of basis, it must happen to all 3 directions the same way. And for the case of polynomials, these are actually symmetric tensors. So polynomials actually are what you might denote sort of sim 3 U, which is a subspace of this. Okay. So I'm not going to go through all of these, but I'm going to go through a couple more. So for an algebra, something different happens, because in an algebra, when I have something like this, what happens is, you can think of sort of xi and xj are inputs, and the thing over here is the output. And so what happens is that actually this thing will get transformed by B inverse, while these two get transformed by B. Okay, and so algebras live in a space that I might denote U tensor U dual. Okay, matrix spaces, if I just have, if I have a matrix space, say A, that's a subspace of n by m matrices, here I can really act on all 3 things separately. So I can act by left multiplying my matrices, I can act by right multiplying my matrices, or I can act by taking linear combinations of my matrices within the space. So here, this one I might denote, oops, now I want this to be different, U, V, W. So now I have 3 groups. I can do 3 independent change of bases here. Okay, and this notation has the feature actually that if you like, you can also use this notation to specify not just invertible, how they transform under invertible change of basis, but under any change of basis. So you can actually specify sort of the full category if you want here. But really what's happening is, this is sort of a shorthand notation for describing how a group is acting on this space. Okay, and these groups, like, why do we like change of basis in linear algebra? Well, because if 2 things are the same under change of basis, they're sort of geometrically the same, right? It just means you chose a different basis to write it down in, but you're talking about the same object. And so it's very natural to talk about isomorphism in all of these contexts. So 2 polynomials are isomorphic if you can get from one to the other by a change of, an invertible change of basis, and so on. And so you could go back at this list and say, well, yeah, these things, they're all different. They have different properties and so on. But you can sort of summarize that by just saying, well, actually, the categories they live in, or the notion of isomorphism, comes from a different group action. The way they transform under change of basis comes from a different group action, right? And this is sort of the old joke about how physicists define tensors that maybe everyone here has heard. A tensor is a thing that transforms like a tensor, because that's their definition. Right. But there's some truth to that. Yeah. Okay. But this raises the question, there are all these different group actions. They represent different kind of objects. Can we nonetheless relate them to one another? And the sort of weak way of relating them is to say, well, I'm going to take, say my polynomial, look at the hypermatrix that represents its coordinates, and I'm just going to treat that hypermatrix as defining for me an algebra and ask, okay, if I know something about the polynomial, what does that tell me about the algebra? And people do that. I mean, people do that, for example, in linear algebra all the time, and you can learn things that way. But it's sort of brittle because you could have two polynomials that are isomorphic, where they're the same up to a change of basis, in this case, acting on the vectors, but that don't give you isomorphic algebras. If you literally just take the three-way hypermatrix and just use it and say, I'm going to use this to define an algebra. So that's why I say that's kind of a weak relationship between these. It's like very brittle. It doesn't preserve the notion of isomorphism. It doesn't even respect the notion of isomorphism. Like it's like very far from being functorial on anything. Okay. So there's a question of, can we give tighter relations between these? Jumping ahead, the answer is going to be yes. Okay, but what is the particular kind of relation we want to use? So it's a particular kind of reduction, which is sort of the computer scientist term, but it's also a morphism, it's also a functor, it's also equivariant, it's also lots of things. And so I just want to give sort of a tentative definition for the purposes of this talk. Like when I say one thing reduces to another or embeds in another, like what do I mean? So I mean, we'll have two spaces with two groups acting on them. So I'll have a group, say G, acting on a vector space V, and a group H acting on a vector space W. So you might think of these, G here might be GLU, and V here might be U tensor U, right? So that was like, this would be actually like non-commutative polynomials, but if you look at the symmetric subspace, it's commutative polynomials. And similarly, HW could be any of the things we're talking about. And we'll say that GV reduces to HW, and I'll use alternately this notation, which is sort of the computer scientist notation, reduces to, or this notation, which is sort of the mathematicians embeds in, to mean the following thing. So it means that there is a map, a function, from V to W with the property that, and these maps will often be like degree 1, but we don't need to require that in our definition. I'm not actually sure I know any examples where they're not degree 1, but I don't see a reason to require that in the definition. With the property that it should send isomorphic things to isomorphic things. Okay, that was sort of the key brittleness that we said above. Yeah.
Could you remind me what is the degree here for the map? In what sense?
V and W are vector spaces. Here, one thing I do want to say is this map is given by polynomials. So like every output coordinate is a polynomial in the input coordinates, right? So maybe I should say polynomial map. Yeah, great. Okay, and what do I want? I want isomorphic things to go to isomorphic things. So I want if V, little v, is equal to GV prime, so this is V and V prime are isomorphic under the G action, then f of V should be equal to H acting on f of V prime for some H. Okay. And so, okay, that's one thing we might want. This is just the thing that says that this is functorial on isomorphisms, if you think of these as functors, or it says that it respects isomorphism, right? If two things are isomorphic, they get mapped to isomorphic things. To be a reduction in the sense of computer science, we actually want it to be sort of a faithful map. So you don't want to take two non-isomorphic things and map them to two things that are isomorphic. So you want to preserve the entire isomorphism class. So we're also going to want the other direction, which is if f of V is equal to H times f of V prime, then there is a G in G such that V is equal to GB prime. So, sort of putting these two together, this would say like V is isomorphic to V prime under the G action if and only if F of V is isomorphic to F of V prime under the H action. Okay, and so this tells us not only can we sort of map our V objects, our V objects into our H objects, but that actually, like, we're sort of faithfully embedding this entire space with its group action into some small part of this space. Okay, so whenever I say reduces to or embeds in, this is for the rest of this talk, this is the notion that I'm going to be using. And this, when I said back up here, an early result I had with Yoming Chow was that K tensor isomorphism reduces to 3 tensor isomorphism. I meant in this sense. So there's some subspace of 3 tensors that sort of faithfully encodes K tensors for any K you like. Now, these tensors, they may have to be bigger, right? If these are K tensors and they're, I don't know, 5 by 5 by 5 by 5, these might be 3 tensors and they could be, 100 by 100 by 100, right? But yeah, okay. All right, so questions about this notion of reduction, because this is sort of going to be the key way that we're going to relate these different kind of objects represented by hypermatrices to one another.
One quick question first is when you said K tensor, does this mean in this context just array, and you're encoding the
yeah. Right, great question. Right, so okay, I should say when I speak, I'm not always precise about tensor versus hypermatrix versus array.
Sure.
In this particular case, when I say tensor, I usually mean, let's see, where should I put this? Maybe I'll just make a little aside here. So when I say a K tensor, I usually mean living in a space that looks like this. And by this notation, I'm also telling you the kind of isomorphism that I want to consider. So up to separate change of basis in each of the K legs of the tensor.
Right. So is that GL1 cross all the...
Right. So this is the group, right, exactly. So this is like GLU1 cross GLUK. Right. So, So I mean, when I say K tensor isomorphism reduces to 3 tensor isomorphism, I mean, if you start with this group acting on this space, you can embed that into the same thing, possibly with larger spaces, but where K is only 3. That's the,
Right.
Okay. Other questions about anything I've said so far, but in particular, I want to make sure people understand sort of what this notion of reduction is saying, because that's, like I said, the key player for sort of the rest of the talk.
So is it right to think that because you always have the identity acting, that these things are necessarily injective? Maybe. Okay, what can I say? In all the examples I know of, they are injective. Okay.
In the definition, it doesn't quite have to be injective.
No, it doesn't. Yeah, that's right.
What this is telling you is that if you look at the map, the induced map on orbits rather than on points, it's injective on orbits.
It's injective. Sorry, yes, that's what I wanted to say. Actually, yeah, it's injective on orbits.
Right. So it's injective on orbits, but like it could take 2 points in the same orbit and send them
and
to
change
one
them
point.
within the orbit. Yeah.
No. Even more than that. Within a single orbit, you could take 2 points in that orbit and map them to the same point in the image space.
Yeah. As long as
You can't take 2 points in separate orbits and map them into the same orbit.
I see. Right. Yes.
Right. So it's slightly weaker than being injective.
Mm-hmm.
Right. Although, like I said, all the examples I know and the examples I'll show you today are all injective.
Mm-hmm.
But I don't have a great reason for wanting to require them to be injective.
Sure.
Yeah. Mm-hmm. Okay. Other questions?
Someone else?
All right, so what I want to start with, because I think people are more familiar with matrices than they are with third order things, is actually a counterexample, a place where there's not a reduction in the case of matrices. And this is, in this notation, so U tensor U star here, this is like matrix conjugacy. So this is the group acting here is like B, M, B inverse. That's what happens under your change of basis. And here, this little wedge 2, this is skew symmetric. So this is skew symmetric matrices. Okay, and here, implied as part of this notation is the group action, which is a matrix over here goes to B, M, B transpose, right? Because that is sort of the natural thing for skew symmetric matrices, okay, which is sometimes called congruence. Okay, and here I claim that actually there is no reduction. This. And to see that, we have to think about what the orbits look like. So for conjugacy of matrices, orbits here are sort of, they're completely determined by, say, Jordan normal form, right? So over here, orbits are determined by Jordan form. Oops, Jordan form. So that is, you can bring every, and here I guess I'm assuming our field is algebraically closed, let's say, but you can bring every matrix to a form that looks like this. So it has blocks on the diagonal. Each block has a single eigenvalue and ones on the off diagonal. They don't all have to be the same size. Some of them could be repeated and so on. Okay. But over here for skew symmetric matrices, the orbits are entirely determined by rank. Oops. So every skew symmetric matrix can be brought to a form which looks like in the upper left corner, you have this, and then you have some zeros, depending on its rank. Okay. So what this tells you is over here, there are only finitely many orbits, right? If we're over an algebraically closed field, the field is infinite, but like it's completely determined by rank. So here there are finitely many orbits. And over here, if our field is infinite, there are infinitely many orbits. Just because of the choices, I mean, even if you only had one eigenvalue, just the choice of eigenvalue gives you infinitely many orbits. And we said above, actually right here, this is saying it's injective on orbits, which means you can't take two orbits over here and map them to the same orbit over here. But here, you can't avoid that because you have infinitely many here, you only have finitely many here. So somehow in the world of matrices, congruence of skew symmetric matrices is like a much simpler thing than conjugacy of matrices, right? It's just rank. Okay, and over here, it's like, well, okay, we still sort of have a full description, but it's a much more complicated description, right? Okay, and even if you want to be a computer scientist about it and sort of say, oh, but I only care about finite fields, so over here, there'll only be finitely many orbits and so on. Actually, what you'll get is even over finite fields, over here, the number of orbits is like n, right? The size of your matrices is just choice of rank. And over here, the number of orbits is going to be like exponential in n, because you can choose how to block this up into matrices, into blocks, and in each block, you separately have a choice of eigenvalue. And so even if you want to say, oh, over a finite field, this is not an issue because there will only be finitely many here, the issue is there will be exponentially many more orbits here than here, which means if you wanted to have such a embedding over a finite field, it would have to increase the dimension exponentially just by counting the number of orbits that you need. Okay, and so from a computer scientist perspective, that's no longer efficient, right? Is like we like things that are polynomial time, polynomial size, and so on. Okay, so even over a finite field, it's like it exists, but or actually, I don't know if it exists. I should say, I should be careful. It could exist, like this is not an obstacle, but if it does, it has to increase size exponentially. Okay, and over infinite fields, it just doesn't exist. Okay, but one of the surprising results that comes out of some of my work with Futorni and Sergeychuk and Yoming Chow is that if you bump these up to tensors and you look at sort of the analog of conjugacy for tensors and the analog of congruence of skew symmetric matrices here, for tensors, there is such an embedding. So, right. So 1/2 of this is what I want to spend the rest of the talk telling you about. And that will sort of give you the flavor for what these embeddings look like. So the original one had 2 steps. And actually, let me make some missing a step here. So the first step is you can reduce from matrix space conjugacy. So that's like, this is like conjugacy of matrices. And then if I add a third different space, this is now talking about matrix spaces up to conjugacy. This reduces to 3 tensor isomorphism. Okay, so that was in my paper with Futorni and Sergeychuk. And then the second step is to reduce from that to alternating matrix space isometry, which is, this is like wedge 2v tensor W. So you now have a space of alternating matrices. Your action is you can take linear combinations of your matrices, that's this one, or you can do the congruence action, the same one that we were doing up here on the matrices themselves. Okay, so when you put these two together, what you get in the context of tensors is that matrix space conjugacy reduces to alternating matrix space isometry, even though if I omit the word space here, no such thing exists. Okay, now, in the original paper with Yoming Chow, where we did this second step, and actually this first step uses sort of a similar gadget. This second step looked like this. This was our reduction, was you start from a 3 tensor, so this is an arbitrary 3 tensor, you're allowed to do separate change of basis on all 3 sides, and you create an alternating matrix space like this. Okay, now I'm not gonna walk you through this, like this is a complicated reduction. I'm showing it to you partly because it's complicated. I'll show you a simpler reduction in a minute, but I wanna highlight a couple things. So one thing is, if you look at the frontal slices, so you slice it sort of parallel to the page, each of those is a matrix. The matrix space I'm talking about is the span of those. And one thing you can see visually here is that each of those matrices will be skew symmetric. So like if you look at the first slice here, what you see is you see a copy of the first slice of my original tensor, and then I put minus A transpose of that here, right? So that first slice is skew symmetric. And then the same thing happens as you get sort of further back in our tensor. Here you have like a little identity matrix. It has 1s here. This one will have -1s here, so that in that slice, you'll see sort of a 1 and a -1. Okay. All right. So I'm not going to walk you through this reduction. The proof of this is like, I don't know, 3 or 4 pages, and we don't have that kind of time. Recently, Yoming and I found a more economical reduction, which is both smaller and easier to prove. And so that's the one that I want to show you. And this will hopefully give you the flavor of like, how do you embed one of these spaces of sort of objects that can be represented by hypermatrices under some group action into another one. Okay, so this is now, I'm going to reduce 3 tensor isomorphism. So that's like, I have some U tensor V tensor W, and I have GLU cross GLV cross GLW acting on it. Okay, I'm going to reduce that to, or embed that in, alternating matrix space isometry. Okay, and this is some wedge 2 U prime, tensor V prime, which the wedge 2 again just means alternating or skew symmetric. So this you can sort of think of as sitting inside of U prime, tensor U prime, tensor V prime. So you're acting on the rows and the columns the same. And then in the third direction, you can take linear combinations of these matrices. Okay, so what does this look like? Actually, the beginning of it is very similar to this picture where you take your original tensor and you just add to each slice a -8 transpose so that everything is now skew symmetric, right? Okay, so the first however many slices are going to look similar. So if this was my original tensor A, then I'm going to put -8 transpose here. Okay, and then behind this, I'm going to have one more slice. And that slice is going to be quite a bit bigger.
So Josh,
But
one
there's
question.
only gonna be- Yeah,
One question about the transpose here. So you're taking the transpose as sort of implied in the two directions, right? Like in the vertical slash.
you're right, just in these directions. So right, so it's yeah, maybe let me unpack that transpose a little. So if my original tensor was like this, I'm thinking of that as a list of matrices, which are these slices. And then I'm taking each one of those matrices and transposing it and putting it down into its left.
Yeah.
All right. So I'm going to do that. And that's just now, okay, every slice is now skew symmetric, right? That's kind of all I did so far. But now the issue is, oh, wait. Yeah, right. The issue is, how do I know that it doesn't sort of mess things up is the issue. So I need some sort of way of saying that when my three tensors were isomorphic, if I had A and B, I'm just sending A to B. Here, if I have two of these things, right? So if I build one of these, and I haven't told you what this last slice in the back looks like yet, but I'll get to that in a minute. But here, if I have two of these, this is now B and minus B transpose. The issue is, okay, if these are isometric as alternating matrix spaces, it's possible that like to get from here to here, I did something where actually I took like some parts of this and I added them onto here to get this. And I don't want that because I want to say this happens if and only if my original two tensors A and B were isomorphic. And in those original tensors, they kind of don't have access to -A transpose, right? It's not like a valid thing to use that. So I need this last slice in back to somehow prevent my isometry, my XX transpose from mixing up this with this. Okay, and the way I'm going to do that, and it's not obvious that this should work, but I think I will be able to prove it to you in the next 10 minutes, is, and here I want to be careful to place things in the right place. Right here, I'm going to put an identity matrix. And then that also means that sort of here, I have to put a minus identity matrix. And then the other thing I'm going to do is in this lower right corner, I'm going to put a very big skew symmetric matrix, just of large rank. So, okay, let me write this out more carefully so you can sort of see what's going on. So my first few slices, if these slices were A1, A2, and so on, my first few slices here look like A1 minus A1 transpose. And then everything else is zeros. Okay, and then I get to the end of that, AM minus AM transpose. Okay, and then my last slice looks like I don't touch this box. So this box has sort of this shape. I put an identity matrix here, minus an identity matrix here, and then a big skew symmetric thing here. So R here is going to be like much bigger than N. Okay, so this is the construction. And then I want to tell you why this works and then talk a little bit about like, okay, what is this sort of telling us about the relationship between 3 tensors and alternating matrix spaces? Okay, so, right, the first aspect of this construction is, so remember, what are we allowed to do? We're allowed to multiply every slice by like an XX transpose. And I'm allowed to take linear combinations of the slices. Okay. The first thing is, if this is big enough, I can't do a linear combination of the slices where I add this back slice to one of these front slices. Because these front slices have rank at most N. But if I add this back slice to one of these slices, then this will show up down here and it'll have rank at least 2R. So if R is sufficiently bigger than N, and it doesn't have to be that much bigger. I think, what do I need it to be? I think I need it to be bigger than something like 2N. If R is bigger than 2N, then can't add this last slice. Let me give this a name. I'll call this gamma for gadget. So I can't add gamma to any of the first slices, the ones coming from A. Okay. Because if I did, right, then you'd get this thing showing up here, and that would increase the rank too much. Okay, so that's good. That's telling me like I added this gadget, but if these 2 spaces, right, and this one gets the same gadget back here. -in, right? So what that tells me is if these 2 spaces are isometric, meaning I can do an XX transpose to get from here, you know, on the left and right here and take linear combinations front and back to get this thing, I can't sort of cheat and like use this gadget slice to help me get A turn into B. Okay, so that's good. And this is a trick that goes back to my paper with Futorni and Sergeychik, where like it's just sort of I've tagged this one thing by its rank. Okay. And now the question is, what happens to the rest? And here we get something sort of funny. So, like, why is it that, you know, I've put these identity matrices in the back slice here? They're lined up with my 2 blocks. But like, why does that prevent me from mixing the blocks? Okay, so here what happens is if you look at what my X has to look like, so suppose that some X sends my alternating matrix space to my other one, where these scripty things are these guys. So this is scripty A, this is scripty B. Okay, then what does this look like? Well, let's just look at what X does to the last slice, to the gadget slice. So it's not quite true that it has to send the gadget slice in A to the gadget slice in B, but it's almost true. And the reason it's not true is because we said, well, when you take linear combinations, you can't add the gadget to any of these because it would increase the rank too much. But you could potentially add one of these to the gadget, and that doesn't increase the rank. Like, we haven't avoided that. The gadget is set up so that if you do that, you can use these identity matrices to cancel whatever you added there and get back to it. So that's like a trick. You kind of, I don't know. If I had 20 more minutes, I could sort of walk through a full example and show you how to do it. But like the upshot is you can't quite assume that this is true, but you can, with one more step, you can then assume that this is true. That like there's some other X that sends A to B that also sends the gadget to itself. Okay, and now here comes the key, is like, what does this X have to look like? So our gadget looks like in minus in 0, and then ir minus, right? This is our gamma. And what does x look like? Well, x, we can break it up into blocks, right? So I could say this here, I have, what did I draw here? 1, 2, 3, 4, 5 blocks. Okay, so I'm going to break up x also into 5 blocks. So I'm going to have a block x11, x15, 5, 1, x5, 5. Okay, and then over here, that same thing but transpose. So x11 transpose, x12 transpose, x15 transpose, 1 transpose, x5, 5 transpose. Okay, and then this is going to equal gamma again. Okay, and now if you look at what's happening in this row, this row, this row, and this row, so just ignore this row of zeros. That set of rows is full rank, right? It's like there are 2n plus 2r rows, and the rank is 2n plus 2r. So for x to do this, on those rows, it has to be full rank. And on this row, because there are also zeros in the same place in gamma over here, that x21 there, like basically this part of the X matrix, has to be 0. Basically, because if it weren't, you would end up with some zeros here, but you can't because there are zeros there on the right-hand side. Okay, and then the key thing is, okay, now, once I know that, I can now go and look at, like, what does X do to the A slices? So I have my X11, X15. I now have a bunch of zeros here. This one actually, 2, 5 doesn't have to be 0, it turns out. It's 3, 1. Okay, so I take this and I look now at what it does to one of my A slices. Okay, and then I have the same thing transposed over here. Okay. And if you calculate that out, what you'll get, if I look at this entry of the input and the output, is you'll get that minus x12 a1 x21 transpose plus x11 a1 x22 transpose is equal to b1. Okay, and so this is basically like, you know, I'm looking at the thing in the 1, 2 block here. So I'm looking at things that sort of line up with that. Okay. But what I just said up here is that x21 is 0. So this tells me x11, x22 transpose is b1. But now that's going to be true for all the a's. So I'm also going to get x11, a2, x22 transpose is b2, and so on. And that's telling me that if I left multiply by x11 and I right multiply by x22, my original tensor, which maybe I'll denote like this, tensor, that gives me my B tensor, x22 transpose. Okay, so that was sort of where the role that these identities played here, and the fact that you had zeros in the gadget here showed up. Okay, all right, so that's the reduction. That's it. So that gives you 3 tensor isomorphism reduces to alternating matrix space isometry. For those of you who got kind of lost in the technical details there, now is a good time to come back. So what I want to talk about in the last few minutes is what does this tell us about the relationship between 3 tensors as objects in the category of 3 tensors and alternating matrix spaces as objects in the category of alternating matrix spaces. And one thing I'll say is it's sort of an open question. Like, it's very interesting to think about this question. I don't have like the answer to this. But one thing you can say is that, like, unlike the matrix case, so remember in the matrix case, alternating matrices, single alternating matrices were very simple. They're just determined by rank. But conjugacy of single matrices were more complicated. They were determined by Jordan normal form. In the case of spaces of matrices, this is just no longer true. That spaces of alternating matrices really, not even all that restricted. It's like this part, this first part, is pretty generic in terms of what a space of alternating matrices look like. The one thing I say is, well, they should all live up here in the upper left block. And if I also look at alternating matrix spaces that contain this one other block, those things are as complicated as arbitrary tensors. Right? And so somehow by having the whole space of matrices instead of just one, it's like you just get way more complexity than rank, for example, right? That you get sort of the full complexity of 3 tensors. Okay. And then again, in the papers with Futorny and Sergeychuk and Yoming Chow, we showed that sort of all of these different things represented by tensors, all of these different spaces, actually there are similar styles of reductions between all of them. So there, in each space, there's sort of a part of that space that's like simulating every other space. And so when you think about things like, oh, I want to think about 3 tensors, or, we were talking earlier about, oh, I want to think about symmetric tensors or partially symmetric tensors. On the one hand, like, yes, working in that particular category has its own value, and like, how do you do the implementation and things like that. On the other hand, what this is kind of telling you is, in general, you're not going to be able to get away with that something that's like significantly simpler for one of these than the other, because there's always some cases in each of these that are as complicated as all of the other cases. Okay, so the last thing I want to end with is a few questions. So one thing we said is these reductions are functorial on isomorphisms. They send isomorphisms to isomorphisms. But there's lots of value in looking at non-isomorphism morphisms, non-invertible morphisms. And so one question is, which of our reductions are functorial for all morphisms, not just isomorphisms? Or can be made to be, right? Maybe they're not sort of functorial as is, but sort of with a little, additional twist, you can make it functorial. Right. Another question is, so one of the things that's happened over the last 4 years is like, as with this example, where like there were 2 very different looking reductions, one of which I just showed you the picture of, this complicated picture, and the other of which I walked you through. These 2 things, while they share some features, like they look quite different. Are they really different, or is there some sense in which they're the same? I mean, obviously they're not the same like tensors, right? Like this one, there's a whole lot more stuff going on. I don't know, when you look at the horizontal slices, you see lots more rank sort of back here than you do here. Like they're clearly different, but sort of spiritually they feel quite similar. And like, is there some sense in which they're the same, or are they really different? And when you start to think about this, one of the questions come up is sort of a self-similarity style question, which is, what are the embeddings of one of these spaces back into itself? So what are the self-embeddings for any of these, let's say, tensor spaces? By which I mean, not just tensors, but sort of all the things we're talking about. And you can ask all sorts of things about this, like, are there only finitely many, up to some sort of notion of equivalence? If there are infinitely many, is there some sense in which they're finitely generated? All sorts of things here. So, we have the groundwork for talking about and building functors between these things. And the question is, sort of, how good can we make this? Or maybe you can't, right? Maybe you can't upgrade some of these to reductions to functors on all morphisms. And then that's now detecting some difference between these spaces, right? Where like, yeah, maybe for isomorphisms, every space can simulate every other, but when you start to look at non-invertible ones, some of these spaces have more information than others, right? So yeah, lots of questions here, both from just sort of the pure math theoretical side to the theoretical computer science side, and also to the implementation side. Yeah, but I will stop there because I think that's what I wanted to tell you about. Thanks.
Well, thank you very much, Josh. Again, run a virtual close. Thank you so much for the talk. I think this is great to see this in motion, so to speak. These ideas. So obviously, I want to open the room for questions. So let me go back to gallery mode so I can see everyone.
Okay, I have a question.
Yes, please, Harm, go ahead.
Yeah. So I wonder about your notion of reduction. So I don't know if you can scroll back to that.
Yeah.
So so you have this like space V and W, and so it's injective on orbits. But I think I would like actually something stronger, namely that, for example, if say FV lies in the orbit closure of FV prime, then V should already lie in the orbit closure of V prime, things like that.
Right. Yeah, and so, okay, one thing
kind of
is,
stronger notion of reduction.
Right, so it's a great question. And as you know, of course, I'm also interested in orbit closures, not just orbits. Yeah, so I've thought about it a little bit, but we haven't really developed it. Some of the things sort of work. So like for maps, like for reductions like the one I showed you, actually, I'd have to think, but I think it also preserves orbit closures. Basically because, if you let me just go to the picture here. Like in this picture, if say B was in the orbit closure of A, whatever sequence of group elements you did to send A to B, you can do sort of a similar sequence here to send this space to this one in the limit. And then the question is, can you also get the reverse, that's an if and only if for orbit closures? And that requires more thought and is a little more delicate. And I don't know the answer, but it's a very natural thing to want, certainly. Yeah, and I should say this definition of reduction is a little bit evolving in time, in that there's a definition of what people call containment in the literature on like wildness and matrix problems. There are actually several definitions of containment. There are several definitions of reduction in computer science, and like the one I chose here is sort of a simplified version. But in our paper, we tried to sort of lay these out and like, what are the things you might want? And but it's not clear that we've settled on the right definition yet. So like another thing that's very natural to want, instead of just existence here, you might ask for some sort of equivariance, where you say, actually, there's a group homomorphism from G to W, and that this H is actually the group homomorphism applied to G. That's another natural thing to want that actually we often have in many of these constructions. So like there are lots of things you could want here, and it's unclear what the right definition is, but yeah, definitely orbit closures is a very interesting thing to throw in there and look at.
Yeah, there's also
one thing. Sorry, one more comment about the orbit closures.
Sorry.
Not this reduction, as far as I can tell. In some of the reductions, I can tell you things like, oh, it takes the whole space and the image of the reduction lies entirely in the null cone. And so like that's bad news from the point of view of orbit closures, potentially, right? So there's also a question of like, yeah, when you have these kind of reductions, what kind of properties do you want to make them play nicely with the invariant theory, for example? Right, so that's another thing. That's something we have thought of, and actually I'd love to talk to you about more about sort of what's happening with these things, because a lot of them, this one I think doesn't, but a lot of the reductions really do end up in the null cone, and we don't know how to not end up in the null cone.
There's this notion also of section and invariant theory.
Right.
So one example is, for example, if you take the diagonal matrices with respect to the symmetric group action, and you can embed that into the n by n matrices with conjugation, and then there's like an isomorphism of invariant rings because of this nice geometric properties.
Oh yes, this is like the Cartan subspace and the Weil group, right?
Yeah, exactly. Yeah. So that's a nice example.
Right.
In that case, it's actually the map is also not injective.
Right.
Yeah.
Right. But it's sort of almost injective up to the action of the Weil group, right? Right. Yeah. So that's another sort of. Yeah.
Right.
Yeah. Right. So no, it's very interesting to think about sort of what is a good notion of reduction that captures all of these things and that plays nicely with them. Yeah. This definition that I presented is sort of a working definition for
Right. So I have a question, and if anyone else wants to ask, please let me know. I was wondering about. I've been trying to, as you were explaining the construction, I was trying to understand intuitively why. I mean, more than intuitively, geometrically, why this might be the case, right? So when you have the case for the matrix case, right? Like the two matrix case where you have conjugation, and so I think that's the slide above. Yeah. So conjugacy and congruence. So the way I understand this, I mean, perhaps from my background in differential geometry, I see U tensor U star as automorphisms or endomorphisms of U, right? In some way, and then I see wedge 2 of V as the two vectors of V, right? So is it right to think that there's endomorphisms of a vector space up to change of basis effectively is larger than the bivectors themselves, because it's just a larger so it's a space of maps, and the other is but it's also a vector space. So I was thinking in terms of I was trying to interpret these spaces as geometrically, and trying to understand why this wouldn't work there.
Right. Yeah. I it's a good question, and actually it's also a question. So one of the things that is maybe less appealing about these kind of reductions is we've sort of now built up this library of reductions and tools for building them and so on. But I don't have a strong intuitive sense for, in some sense, why they work. I mean, I know the proofs, and like we clearly have built up some intuition about how to build these gadgets and things, because like we can now sort of do it with some regularity.
Sure.
But yeah, I wish I had a geometric understanding the way you say, even for, I mean, this one looks complicated, but even for something like this, like what geometrically is happening here? What geometric objects do these correspond to? There should be, like, maybe there's sort of a basis-free way of talking about these, and that would clarify things, but we've thought about that, and it's like, you can write it down, but it's not clear what it's telling you. And and up here, it's like, well, yeah, you can think of, okay, this is some endomorphisms of a vector space. This is just bivectors. But like, why are bivectors simpler? I don't know, because they're only finitely many orbits. But when you start to talk about trivectors, it's still just trivectors, but like, this is no longer the case. Trivectors are now universal for tensor isomorphism.
But I think...
And so, yeah, I don't have a good geometric sense of like why some of these things should be true, I guess.
Yeah, I think.
But it's a great question.
Yeah. Like in the case of, because you really have wedge 2 and then tensor the other space, right?
Right. So in these cases, right, it's it's like wedge 2 tensor the space, because you have a space of skew symmetric matrices.
Right. Because to me I don't know, I have a feeling that, intuitively it kind of makes sense to me that you can't embed you can't represent somehow or like reduce in the sense that you're introducing the full vector endomorphism to just the structure of vectors, because in some sense, I mean, vectors live within the space in a way, and it's, I mean, because it's vectors up to change of basis in the same way. Right.
Yeah.
So in a way, to me, it makes sense that full endomorphisms cannot reduce to just vectors, because vectors are sort of these oriented planes in your vector space. And then, but when you do, so what I find intriguing, I guess, is that wedge 2 tensor W that is somehow creating this extra room where you can build stuff, and then, but if you did wedge 3 of V or something like that, then probably wouldn't work, right?
Right, that's right. So, well, for wedge 3, that was in a separate paper with who was then Yoming's student Gang Tang. We also get a similar reduction.
Oh, really?
So,
So
like,
it does
we call
work.
these problems TI complete, is like, that's sort of the CS language, like NP complete or GI complete for graph isomorphism.
Right.
So yeah, wedge 3, like trivector isomorphism, is also TI complete.
Okay.
And so, like, yeah, that's the other thing that these geometric questions come up against, is like any geometric intuition you have for the matrix case or for any of these cases, it's like, well, why does that geometric intuition suddenly break when you go up to 3? Right? Yeah.
Well, that's a very, I mean, that's a very common theme I found. I mean, whenever you go to this next rung in the ladder, and it's already kind of like out of control. It's like, to understand. I mean,
Yeah.
Any more questions? Any more comments?
Let me hear Luke's talk, because
I'm here and ready whenever you are.
Yep. So unless there are more questions, we can also discuss a little bit after Luke's talk. We'll have a lot of time after that.
Yeah, and I'm also, I mean, I'm sort of in and out all week, so I'm happy to talk with people in the middle of the week too.
Oh, perfect. Yeah, that'll be great. So yeah, we'll be in touch for that. So yeah, Luke, maybe we can go ahead.
Sure. So I'm going to try to use 2 devices at the same time. If it fails, I will switch. But let's, and I realize you'll be looking at the top of my head a little more often if I'm looking down. But anyway, let's see if this can work, if sharing is available.
Yep.
It's all visible for everybody. It's okay. Okay, good. Okay, well, thanks again for the opportunity to participate in this workshop and speak to you. I'm gonna, I have too many slides, so I'll apologize for that in advance, but tell you about a theme measuring entanglement using algebraic geometry. And this work was carried out with Frederick Holwick, who's at UTBM in France, University of Technology Belfort-Montbéliard. And nearby is the Alsace region, and this is my daughter on my back. We hiked up this mountain with my wife. She's 6 now, so we probably won't try this. We're going to be there this summer. We have 2 more kids, so but we're still, I think we're going to go back and try this hike. It's
Nice.
a beautiful view. Okay.
I thought you were going to say try and reproduce the picture with her in the backpack as a 6-year-old.
Yeah, that would be tough. Anyway, so here I wanted to start the talk with a couple advertisements for some of the work that this talk is motivated by. One of them is about hyperdeterminants, which is the hypermatrix analog of a determinant, or one analog. Dr. Fred Holwick and I studied what you could get from E8 as a Lie algebra in terms of hyperdeterminants, and it turns out you can get several different hyperdeterminants from this, some which were known and some which were not. The Rubik's Cube picture is supposed to tell you exactly how to produce singular tensors, which have 0 hyperdeterminant, just like singular matrices have 0 determinant. So you take your hypermatrix, you pick a corner, you zero out everything that emanates from that corner on all of the axes that share the corner, and then let the rest of the entries be anything. And that is a singular hypermatrix. And then you could change coordinates arbitrarily in each direction, and that would still be singular. And this is the root lattice for E8 projected into the plane, which I find very beautiful. Okay, so at some point I will try to draw, so let's just see as a practice. Okay, I can draw like this. That's a little bit not dark. Okay. Just checking to see if these are visible. Okay. Okay, cool. So I want this to go away. How do I make this part go away? Oh, there, that's fun. Okay, good. Okay, I want to advertise one other piece of, one other publication with a then PhD student, Hamza Jafali. He's now working for a quantum information lab, a quantum computing lab in France. And he visited Auburn for a couple of months. It was a really fruitful visit. We started with the idea of like polynomials are functions that you can evaluate, and so are neural networks. So could we use a neural network or train a neural network to behave like invariants that we like for tensors that are too hard to compute in terms of the entries of the tensor, or monomials in those entries, I mean. And I just give you one snapshot of a type of network that we used and trained, and then like some of the architecture, training, accuracy, and validation. The upshot is that even for these 2 by 2 by 2 by 2 by 2 tensors, we can detect singularity of tensors, so, you know, this accuracy, which we don't know how to write down that polynomial that gives the same result, but we can evaluate it at as many points as we want, and therefore we can train a network to sort of mimic that polynomial or approximate it. And I encourage you to check that out, and I can tell you more about that at another time if you like. Okay, so let's think about order 5 tensors, 5 axis tensors or 5 arity tensors. And we're interested in tensors that have rank 5. They can be written as the sum of 5 rank 1 tensors, or limits thereof to get an algebraic variety. And you might just want to know, like, how do I detect this rank 5-ness? So the most naive thing you could do is just check to see if there are any linear functions that vanish on them. It turns out there aren't. There are 32 variables. So in this portion of the table, you see in degree 1, there are 32 variables, 32 linear forms, and none of them vanish on the set. So the dimension of the ideal in that degree is 0. This is the Hilbert function of the ideal of this algebraic variety. Then you could guess, okay, well, let's check. Okay, I know how to do linear interpolation, so maybe I just do quadratic interpolation, but just interpret that as linear interpolation in the 528 quadratic monomials in the 32 variables. And you find that there are no quadratic polynomials that vanish on the set either. For theoretical reasons, we know that you have to start in degree above 5. So, but if you had tried it, you would be dealing with linear algebra on 376,000 dimensional vector space, which is pretty hard. And moreover, if you go to the first place where you could expect there to be non-trivial equations, you find precisely one polynomial out of the 2.3 million polynomials in the space in that degree that vanish on the variety. So linear interpolation is successful in low degree and low number of variables, or low number of monomials if you want to do it in higher degree. But after that, it becomes very difficult, and you must use symmetry. And it's not just like the symmetry of permuting the indices, but really the symmetry by change of coordinates in each direction. And in fact, there's a few other numerical tools which we used. We did not do computations in a 500 billion dimensional space, but we were able to write a function that evaluates this degree 16 polynomial, and prove that it's not 0 and vanishes on the rank 5 tensors. And with a few other tools of algebraic geometry, we're able to show that this variety is actually cut out by these two equations, one in degree 6 and one in degree 16. So I'm very interested in these kind of high-powered computations that are impossible to do without symmetry, and this is one example, which I enjoyed working on very much.
Luke,
Yes.
is that, do you know, is that just set theoretic or like that generates the whole ideal?
So I put a star in the theorem because we used Bertini at one point, and Bertini is a piece of numerical software that produces results like the degree of this variety is degree 96 with the precision and confidence we have in the computer and the developers of that program. And then once we know that variety is degree 96, suppose we knew that unconditionally, then we have an ideal theoretic proof that the affine cone of this variety is cut out by degree 6 and degree 16 equations. This is the ideal theoretic statement.
Nice, nice.
We know very few of these. So for the people that are not in the algebra world, it's, there's two different things. You could cut out the set as a zero set of polynomials, but you could also generate the ideal of all functions that vanish on, all polynomial functions that vanish on the variety. Those are significantly more challenging to solve the ideal theoretic problem than the set theoretic one, and we know almost nothing about low-rank tensors, to be honest, in complete generality, but this is one new thing that we were able to find out. So that's for rank 5, and in the previous slide I mentioned, for singular is something different. It's a degree 128 polynomial on 32 variables. We don't have any hope to interpolate and find an expression of that polynomial, but the neural network could actually answer the question, which we're trying to answer here, which is like, how do I give a test for detecting whether the tensor has this property, in this case rank 5, in the other case singular. Now we have a test to evaluate this degree 6 equation and the degree 16 equation. If they both vanish, the thing has border rank 5 at most. If one of them doesn't vanish, it does not have border rank 5. Okay, so I said algebraic geometry and quantum information, so I want to give you a little bit of a library between the two worlds of quantum information, QI, and algebraic geometry, AG. So in quantum information, the researcher studies Hilbert space, which we think of as Cn+1, and unit vectors in that space, which are represented by these ket vectors, by these kind of ket vectors like this. Okay, and norm we write as the bra paired with the ket, or with the inner product. In algebraic geometry, we study projective space, which is the elements are actually lines through the origin, and we represent them as vectors up to scale with the square brackets. Likewise, in the Hilbert space, we have a measurement basis represented by just the numbers 0 through n in the ket format. And in algebraic geometry, we think of variables indexed by 0 up to n, so x0 up to xn, as a basis of the vector space. In quantum information, they often want an orthonormal basis. Algebraic geometry sometimes ignores the angle information, so maybe we just care about having a basis, maybe not orthonormal. And similarly, quantum information likes to use the complex inner product, and algebraic geometry wants to avoid doing things that aren't algebraic, like taking the complex conjugate. We may still have many things in common, but those are some things that are not. When we deal with a tensor space in quantum information, where we just concatenate the ket vectors, and that gives us a basis of the tensor product space. In algebraic geometry, maybe you actually write the tensor symbol between tensor product of variables as the basis of the higher tensor space. A state in the quantum information setting of an M particle ensemble. So you imagine M electrons or M other particles, then the state is just going to be a vector in the Hilbert space that has norm 1. A vector, in the Hilbert space is actually a tensor product of Hilbert spaces. And in algebraic geometry, the analogous thing is just a point in projective space still, but maybe the dimension of the projective space is larger. The simplest possible states that you could have are these product states that are called separable states, and in algebraic geometry we call those just pure tensor products. So you take a bunch of vectors and take their tensor product, those are the rank 1 tensors. Okay, so many things are like just directly translate from one world to the other. So a key concept in quantum information is entanglement. So let me try to give you the simplest example of entanglement and not entanglement. So we'll say a particle ensemble is entangled if you can write it as the tensor product of a bunch of vectors. And they satisfy this independence condition. So the independence condition is this one here. This one here, that the conditional probability is just the product of the probabilities. So let's do this example. So let's take the state, it has to be a unit vector. So this state here, 1/√2 times the vector 0, 0, 1, 1. I think most of us may be more familiar with the notation like the matrix notation. So this is the matrix like this, right? With the 1/√2 in front to make it unit norm. Okay, and then the 0, 0 and the 1, 1, you could think of those as the keys in the sort of hash table array sort of notation. Those are just the keys, and the coefficients are the values. Okay. So if we try to measure this one particle at a time, that means project onto either the first direction, first axis, or the second axis. The probability of measuring a 0 in the first axis or the first direction is 50%. And it's the same as the probability of measuring a 1 in the first direction is also 50%. And likewise in the second direction, same probabilities for zeros and ones. So let's check the conditional probability statement. So the probability of measuring a 0 if you had in the second register, if you've already measured a 0 in the first register, is actually 100%. So you imagine okay, and then likewise, if you had already measured a 1 in the first register, the probability of measuring a 0 is actually 0%. Okay. So this fails the independence condition. And if you're keeping track, I feel like we should think about this condition here as, well, take the difference between the left-hand side and the right-hand side, and it looks like a 2x2 determinant. And that's actually the invariant that determines whether a two-particle state is unentangled or not, is the determinant. So here's the case in the determinant, in terms of this remark here. If you just look at the determinant of the ket 0, 0, this one here, well, it produces the matrix with a 1 in the upper left-hand corner, so certainly the determinant of that matrix is 0. And it turns out that that's equivalent for any matrix that you get out of this. If the determinant is 0, then it's unentangled. It's a pure outer product. Likewise, the other state is a rank 2 matrix, and certainly the determinant is not 0, so that's an entangled system. Okay, this is the most basic example. If there are any questions, feel free to go ahead and stop me. Sometimes the notation is the hardest part of this, but the concepts we've known for a long time, I think. Okay, so rank 1 tensors for the algebraic geometer are just points on the Segre variety. It's a projective variety whose points are outer products of vectors. And I just list them like A tensor B tensor up to C. And ABC are points in projective space with brackets, meaning I only care about them up to scale. And this is really the natural place to study rank 1 tensors, because the tensor product, well, the scalars can move across between one vector and the other. So I really only care about A, B, and C up to scale. And so the Segre product really makes sense for the rank 1 tensors. But the quantum information theorist calls these separable states or product states or unentangled states. Nice to know the Segre variety, its ideal is generated by the 2x2 minors of the flattenings of the tensor, which we saw in the first talk of this sort of unfolding operation to make the tensor into a matrix, and take all the 2x2 minors of that and every way of unfolding the tensor. Those polynomials define this variety and actually generate its ideal. The other thing that's nice about this is it's a homogeneous variety, means it's the orbit of a single point up to the action of this product of SLn plus 1. So the quantum information theorists call this group the Slock group, which tells them how to transform between one system and another. And we know the dimension of the variety, and so on. There's a lot that we know about this set. Okay, so more things that we could study from one side to the other. Well, bosons represent a certain type of particle. As the quantum information theorists, they call them bosonic systems. The algebraic geometer calls them symmetric tensors. Okay, and the separable states are just the tensor product of a single vector with itself d times. The algebraic geometer knows that as the Veronese variety, or the variety of powers of linear forms. Take any linear form, raise it to the dth power, and consider that up to scale. That gives you the points of the Veronese variety. On the other hand, there are fermionic systems, which consist of particles that can't occupy the same state at the same time. The algebraic geometer studies skew-symmetric tensors that have the same property. And fermionic product states correspond to points on the Grassmannian, which are pure wedge products of vectors. Or I heard in the last talk bivectors and trivectors. Well, these are the pure bivectors, just the wedge product of two vectors for bivector, or wedge product of d vectors for higher d. And in the quantum information setting, maybe they would think of this as the slot group applied to the ket vectors 0 up to n-1 in this case. They also have something called creation and annihilation operators, and when you add that to the mix, the set that we consider is on the algebraic geometry side is pure spinors, or the states live in the sort of representation of the spin group, and the pure spinors represent the sort of product states. Okay. We have a paper on a hyperdeterminant for fermionic Fock space that you could check out, but I'm kind of giving an overview of the whole program, so it's just kind of part of the story. Let me tell you just more about the symmetric side, just to give the description sort of in both worlds of these symmetric states. In quantum information, they have a special basis called the Dicke basis, and we list this below here. So the first basis vector is just 0, 0, 0, 0, and for the algebraic geometer, that's x to the d. And then as you go down, you have to keep norm equal to 1, so you divide by this square root of a binomial coefficient, and then add up over all the ways to have the same number of ones, perhaps in different places, and that corresponds to a monomial x to the d minus k times y to the k. So for the quantum information theorists, the bosonic states for sort of a two-state basic particle correspond to binary forms, and algebraic geometers know a lot about binary forms, and this sort of dictionary going back and forth can be quite rich. You can expand the number of states that you allow each particle to have, and then you would have polynomials, and you think about the monomial basis of the space of polynomials as your sort of replacement for the Dicke states on the quantum information side. Okay, let me skip the first half of the slide and just say that one thing we care about is for a given state that doesn't have rank 1 or isn't unentangled, we would like to know how far away is it from being unentangled. And we would like to know the states that maximize this distance. So in algebraic geometry, they call this concept the Euclidean distance degree, counting the number of points that maximize this distance function from the algebraic variety. So this topic got popularized probably 10 years ago, and there are several papers on the Euclidean distance degree of an algebraic variety. They're highly connected to another concept called eigenvectors of tensors. These are the critical points of the distance function when you're dealing with symmetric functions, symmetric tensors. So while the quantum information theorist studies the closest product points, maybe the algebraic geometer studies the Chow variety of products of linear forms. These are also called the separable states. And there are many ways to measure entanglement, and one of them is called the geometric measure of entanglement. I wrote the formula for it here, but it's the sort of like a max-min problem. You take a point in space and you find the point that's nearest it on the variety you care about, and that's a minimum. And the maximum of the geometric measure entanglement would be those tensors that have the most entanglement. We're interested in finding those tensors. And we have some results in the symmetric case you could try other notions of measuring entanglement as well that are based on invariant theory. Okay. So let's go back to hyperdeterminants. Our mantra here is going to be to use algebraic invariance to separate entanglement types. And while algebraic geometers like polynomial expressions, I think that, at least if I'm speaking for myself, I'm okay with evaluation methods like straight line programs or sort of arithmetic circuits or so on, because if my only goal is to determine whether a point lives on a particular algebraic variety, I'm okay with just evaluating the point at the polynomials that define the variety. I don't actually need to write those polynomials down to answer that question. So the determinant is a perfect example of this, and I'm teaching honors linear algebra this semester, so I have told them many times, like, the determinant is an incredibly complicated polynomial, but it's actually very easy to evaluate. It has n factorial terms, but you can sort of escape computing it in around n to the fourth operations in a very naive implementation of Gaussian elimination. So n factorial versus n to the fourth is really a huge speed up, and if you ever have to compute anything larger than a 4x4 determinant, you should probably use Gaussian elimination. Well, you should actually have Wolfram alpha computed or something, but like, if you had to do it by hand and the world depended on it, then Gaussian elimination is probably your friend. Hyperdeterminants and other invariants, there is a mantra that people have based on a paper of Lim and Hiller called most tensor problems are NP hard, and I wanted to chime in at the end of the previous talk of this dichotomy between like matrices and then third order tensors, and like the whole world just flips on its end. Almost all of the matrix problems you can imagine are polynomial time computable in the size of the matrix, but then it seems like most of the things you want to do in generalization to third order tensors and higher are NP hard to compute or sharp P to like actually count or so on, and yet it's not actually always known whether, say, the hyperdeterminant is actually NP hard to compute. I think that may be still open, and at least in some cases. So it might be possible that these hyperdeterminants, which I'm going to describe, are extremely complicated but can be easily evaluated. Okay, so let's see some examples of this. Before that, I want to just give you the freshman orientation for hyperdeterminants. Like, how do we generalize the concept of determinant to hypermatrices? So first, I need to give you a reinterpretation of the determinant. So a matrix will have rank 1 if, up to Gaussian elimination, there's a single non-zero entry in the matrix, and we might as well put it in the upper left-hand corner of the matrix, but it has rank 1 if it's a column times a row, and we can pick our favorite column and row, which is just the first basis vector in both the spaces. The dual of this concept is a matrix will be singular if, up to Gaussian elimination, you can either get a row of zeros or a column of zeros, or both. And the set of all the singular matrices, it turns out, is determined by the vanishing of the determinant. So probably not the first way you saw the determinant. I didn't describe the polynomial for you. I described its zero set. It's all all matrices that have the format that, up to Gaussian elimination, they have a row or column of zeros. We can do this in the hypermatrix setting. So the Segre variety is, up to change of coordinates, all the points, all the hypermatrices that have zeros everywhere except for a single entry. We might as well put it on the corner. Those are the rank 1 tensors, up to change of coordinates. Then if I want to know what's singular, I need to compute the tangent space to that space, because the dual variety is going to be the set of all hyperplanes that are tangent to the variety. In coordinates, I see it this way. The tangent space to this is just all of the tensors that are zero everywhere except for on the same row and column, as I mentioned in the introduction. So these are the only sort of places in the tensor that are not zero, and everything else is zero. Okay, so and then the hyperplanes that are tangent to this is just literally the opposite space, the orthogonal complement of that space. So it's all the hypermatrices that have So I said all the non-zero entries are in red in the tangent case, and I just swap 0 and non-zero to get the orthogonal complement. Okay, so if you want an arbitrary number of points that are on this hyperdeterminate locus, you just choose a corner, zero out everything coming from that corner, put everything else as random numbers, and then change coordinates on the faces of this hypermatrix to get an arbitrary point on the hyperdeterminate locus. I didn't tell you the polynomial, but I told you as many points on it as you want, and as many points as you want that vanish on this polynomial. So those are the things that are in algebraic geometry, the projective dual. So going back to matrices, the matrices whose determinant is not 0, we're thinking of those as the furthest away from the rank 1 matrices, and those are the most entangled biparticle systems. So in a very real sense, the tensors for which the hyperdeterminant does not vanish are going to be one way of calling something the most entangled. But there's more than one way to try to say something is the most entangled. So here's the most classical non-matrix example. So in the middle of the page, you see the tensors that these are the orbits of the binary, 2 by 2 by 2 tensors, third order, 3 arity binary tensors. There's only 6 non-zero orbits. The top is this point of rank 2, and then at the bottom is the point of rank 1, and then 0. There's a few things in between. So the algebraic geometers know this in terms of secant varieties and Segre varieties and singular locus of the tangential variety and so on, but there's a similar picture in algebraic geometry. And the top of the picture is this tangential variety, which is also the dual of the Segre variety. It's the hyperdeterminate locus. It's a hypersurface in P7 and has a degree 4 equation, and we know a lot about it. So now I want to give you a construction that simultaneously computes the hyperdeterminant for 3 different settings: the fermionic setting, wedge 3c6, the 3 qubit setting, c2 to the 3, and the symmetric, binary forms of the symmetric or the bosonic case. Okay. So we're going to construct a non-Lie algebra. It's an algebra that doesn't necessarily have a skew commuting product. It has a somewhat skew and somewhat commuting product, so it's not a Lie algebra. But nonetheless, it's a graded algebra. I'll take SL6 and I'll add to it wedge 3c6, and I'll call SL6 the 0th piece of the algebra. Wedge 3c6 is the first one piece, and then it's Z2 graded. For any algebra, I can compute the adjoint operator of the algebra just by saying what every product goes to. So if I take a T in wedge 3c6, I can ask, what's the matrix representation of the adjoint operator? Well, just tell me what T does to every basis vector, write the answer in terms of bases, and I get a 55 by 55 matrix with some block structure. And it turns out I could just take that matrix, compute its 4th power, compute the trace of that, which would be a disaster if the matrix was filled with variables, but I'm going to do this for a particular tensor that has numbers in the array and not just variables. And that gives me this invariant called F4. Working on releasing, I think if you look on my GitHub page, you'll probably see this package, exterior extensions, available to the public. You can try it out. So here's another nice thing. Well, the space C6 can be written as a direct sum of 3 copies of C2, and I can name those copies. And if I take the 3rd exterior power of a sum of 3 things, one of the things that's in there is just wedge 1 of each of them tensored together. And since they're all disjoint, I can call that wedge product a tensor product. And then one of the things that's inside of this space, well, is the symmetric tensors living inside of the space of tensors. If I think in terms of variables, I could specialize the variables that are representing the tensors like xi, j, k, skew symmetric in their indices. Here, I could specialize them to just represent the ones that are only used, like 1, 1 and 3, or 1 and 4 in this case, I guess I used start from 0 before. So, okay, so I can imagine this copy of C2 as being the one that works with 0 and 3, and then the next one that deals with 1 and 4, and the next one that deals with 2 and 5. Okay, so I have basis vectors that represent those C2s. And so it turns out that I can just take this invariant that I computed over here, this trace of the 4th power, this 55 by 55 matrix. And if I restrict the variables, plug in something from their space, I actually get the 2 by 2 by 2 hyperdeterminant. And if I think of that 2 by 2 by 2 hypermatrix as really being, if it's symmetric, if I put a symmetric matrix, a symmetric tensor there, think of that as the coefficients of a binary form, a cubic binary form, then plug that into this invariant and get the discriminant. And I can check this for a couple of states. So the state T that I've listed here is a point in that tangential variety. And it turns out the hyperdeterminant there is just 0. And then this point H, which is a point on the open orbit, is the hyperdeterminants of having value 36, and so it's not on the tensors of order rank 2 set. It's outside. So the cubic polynomials, or the points on the secant variety, or the points on the sum of secant of Grassmannian, have non-vanishing hyperdeterminant, and so they're far away from being unentangled. Okay, in this one slide, I told you like a whole paper, so I realize it's super dense, but you can imagine changing some of these numbers around and getting similar kinds of invariants for other tensor spaces.
Luke,
there are many details, but
is there a, like, aside from just say checking that the restrictions are non-zero and like happening to know that the invariant ring for those smaller spaces is only generated by one thing, like is there something about the relationship between the groups and the spaces or something that you should expect this behavior in terms of the invariance? Or like, is this just kind of a coincidental, like, I don't know, law of small numbers miracle kind of thing?
Yes. The answer to your question is yes. both happen, okay? So I'll show you some of the law of small numbers examples that come up and just happen to work. But in the paper with Holleck called Jordan Decompositions of Tensors, we try to explore exactly this question of like, when does this construction produce something interesting? So the point is, you take your space of tensors, it should not have a Jordan decomposition. There's no concept of like it's a matrix up to similarity, similar to the Jordan canonical form. But if you embed your tensor space into an algebra like this, then the invariance of the algebra will be invariance for your tensor if you do everything correctly. And there's a lot more for us to learn about that. Let me say that, and then we can come back to that question after you see a few more examples. Okay, so if you were lost on the previous page, I just want to give a high school example. So, or even elementary school. I feel like some people may have learned this in elementary school. At least we learned the quadratic formula x is equal to negative b plus, or this like nursery rhyme version, the quadratic formula. The discriminant b squared minus 4ac, well, I flipped it around, but the b squared minus 4ac is the discriminant. It vanishes when the original polynomial had a double root. But you could actually imagine the coefficients here as being the entries up to scale of this matrix, right? So a symmetric matrix corresponds to the coefficients of the quadratic polynomial. And I moved the 4ac, I moved the 2 by changing the coefficients, but it's the same concept. The determinant of this symmetric matrix is equal to the discriminant of the polynomial. Again, with the caveat of rescaling some of the coefficients. You could also project this to the space where b equals 0, and then try to interpret what the determinant, well, what is the discriminant now? If I put a 0 here, then the discriminant is just ac, and it vanishes whenever either a or c is 0, i.e. when f is either x squared or y squared. And up to change of coordinates, it vanishes whenever f is a pure power. Okay, just rank 1 diagonal matrices. And when you sparsify your invariant, you're actually projecting that polynomial called the invariant to a smaller space. Okay, that's the absolute simplest example of what we're doing here. We're going to take an invariant defined on a bigger space, and then we're going to describe it on a smaller space. So let me skip this page. This is a way to also compute the determinant, a hyperdeterminant with Schlafly's method. So I want to give you some more of these law of small numbers. Well, the numbers are not so small, but law of small numbers, situations where you can use the strategy. So back in the 70s and 80s, Vinberg and company developed a set of tools that allow us to, from my point of view, embed a space of tensors into an algebra. From their point of view, they were maybe interested in the algebra E8, but in fact, what they were able to do with several other authors said, like, let's take this wedge 3C9 space. What are the orbits of SL9 in that space? And Vinberg noticed that you could classify the orbits in that space by actually classifying the nilpotent orbits in this larger algebra called E8. It's a vector space with a product, and the product is somewhat complicated. I find this description of E8 a lot easier to understand what the product should be. But there are a few other examples. E8 could also be decomposed into a Z2 graded algebra where the 0th piece is actually the spin 16 Lie algebra. The G1 is just the even exterior powers, and that is part of some Clifford algebra. Antonian is another one in the sort of school. They noticed that the Lie algebra for E7 has the decomposition of SL8 plus wedge 4 C8, and therefore you get a classification of wedge 4 C8's orbits under SL8 by classifying the nilpotent orbits of E7. And this is a long story. It depends on Dinkin's classification of subalgebras of semi-simple Lie algebras. You can see these in the references. But the nice thing here is that we get equivariant projections from E8 to some of the spaces where our quantum information theory states live. And now maybe that sounds worse because E8 is this 248-dimensional Lie algebra, or E7, these are big things, and I'm projecting to something smaller. But I gain something because I can view my tensors as living in an algebra where there's a Jordan decomposition, and essentially that allows me to get the classification. And I think I put this on the next slide. There's something called the Chevalier restriction theorem that says that the invariants for the algebra are the invariant ring is just equal to, I should say isomorphic to, the invariant ring on the Cartan with respect to the discrete group called the Weil group. So we changed the problem from a continuous group on a bigger space to a finite group on a smaller space. So that's a lot easier. And also there's this really neat theorem of Tevelev that says when we're in the situation that we are in, where we have a group, complex semi-simple group, Lie group, and we consider the adjoint orbit, then the dual variety, this hyperdeterminant locus, has a very simple description when you restrict to semi-simple elements. So semi-simple elements are defined because we have a Lie algebra, we can have a Jordan decomposition, and the semi-simple part is something we could actually imagine computing. And the description of this invariant is just the product of the roots. So I want to say that this is just a very high-powered version of a statement that we all learned in our freshman linear algebra class called the determinant is the product of the eigenvalues. Okay, so if you replace like roots of the Lie algebra with eigenvalues, then this hyperdeterminant is the product of the roots. And like in linear algebra, there's not a single change of basis that puts every matrix into semi-simple plus nilpotent, or just gives you the eigenvalues of the matrix on the diagonal of a upper triangular matrix. But you could imagine a generic semi-simple matrix as just a diagonal matrix, and then for the generic semi-simple matrices, the determinant is just the product of the diagonal entries, and that makes it very easy. This is the idea behind Gaussian elimination as well. And so in these settings, we can actually evaluate the invariance for the bigger algebra, G, which is going to be E8 in many cases, as the product of roots. It's just a product, a very simple description. Okay, so here's how we do it in practice. Let's list the semi-simple fermions coming from E8. So they're going to be fermions in wedge 3C9. So we view E8 with the Z3 grading. It has a root system that reflects the grading. So this is the way we describe it, EI minus EJ. Those give me the roots for SL9. And then I have more roots considered, these sums of three distinct epsilons or E's. The Cartan elements, or the semi-simple elements, or the maximal diagonalizable subalgebra is, well, we can take a different Cartan than you usually take for E8, so that the part of the Cartan actually lives in this wedge 3C9. So we pick one where half of the algebra lives on one side and half lives on the other side. And this Cartan subalgebra, the S1 half of it, has the following basis, and these also have nice combinatorial descriptions of in terms of Steiner triple systems. But anyway, we can then write a generic semi-simple form, which would be the analog of your diagonal matrices. Think of the p's as vectors and the z's as the coefficients, and then consider this equivariant projection from SL9 from E8 to wedge 3 of V. V is C9. And then we can restrict to the semi-simple parts. Since Tevelev told us that the E8 discriminant that we care about is just the product of roots, then the discriminant for wedge 3 C9 would just be the product, well, restricted, the product of the restricted roots. Okay, so the Jordan decomposition is how to fit this invariant, which is extremely complicated, onto one slide. If you embed your tensor space into this algebra, you can interpret tensors as being either semi-simple or nilpotent, having those parts, if you can do that in the Lie algebra. And a nice fact is that if you have a continuous invariant, the value of the invariant only depends on the semi-simple part. Just like the determinant really only depends on the eigenvalues, not on the rest of the matrix. Like not on the nilpotent part of the matrix anyway. That's true for any continuous invariant where you have this Jordan decomposition. So it actually does make sense to just evaluate the continuous invariant on the semi-simple part. So the discriminant, there are 240 roots for E8. When you restrict to this S1, you actually get a polynomial to the 6th power, and the root, 6th root of that polynomial is the one you see here. And you can read off, maybe this part's a bit hidden, Z1 is one of the factors. So if any of the eigenvalues of the matrix are 0, the determinant is 0, the same property here. If one of these coefficients, Z1, Z2, Z3, Z4 are 0, then the hyperdeterminant is actually 0, and then there are these other linear forms sitting here. So knowing that the restriction of the E8 discriminant to these Grassmannians or these fermions is equivalent to knowing that it does it on semi-simple parts. So because of this proposition. We have several other formulations for this in our paper. So the polynomials are insanely complicated, but when you restrict to the semi-simple part, they become very manageable. Here's how you get spinors from E8. So in Antonio and Ilishvili's 82 paper, they give this description of, you take fermions, but you allow creation and annihilation operators to change the degree of the tensor by, or adding two particles from a vacuum. And then you just play the same game. You list the roots of the Cartan in a way that allow you to put some of the the Cartan living in, respecting this decomposition anyway, and you can restrict to the semi-simple parts. In this case, there's a Cartan that lives fully in here, an 8-dimensional subspace that lives in the other part of the algebra. And so we have generic semi-simple spinners. The notation is somewhat complicated, but the story is the same. And so we can evaluate the Tevelev version of the hyperdeterminant, and I had to shrink the formula slightly, but this is the hyperdeterminant for fermionic Fock space in this case, when you restrict to semi-simple parts. So you see that the fermionic Fock space hyperdeterminant vanishes when any of the semi-simple, coefficients in the semi-simple parts vanish, because we have the product of the variables here. But then also there's all these other linear forms which you can think of as coming from the roots. Okay, so that's a formula we're proud of. Let's see, how long should I go until? We originally scheduled till 3, but we started a little bit late.
Yeah, we can take 10-15 more minutes, and then until 1/2 for discussion.
Okay. Sorry, I unshared the screen. Okay. So there we go. Okay. So in our paper on hyperdeterminants from E8, we gave the rectangular part of this diagram that show all the different invariants that we could get from the E8 discriminant, including many types of hyperdeterminants that were either known how to compute and some which were not known. We did not know how to compute them. And we added this spinner variety case just recently. Okay. Another thing we could do with invariants for tensors is we could try to write high degree invariants in terms of the basic invariants. So in the cases that I've put on the slide so far, there's the invariant ring is finitely generated. And so we could ask this, in the case of wedge 3C9, there's a degree 120 invariant. That's the discriminant or the hyperdeterminant. It's the square root of the discriminant for E8 when you do the restriction, but maybe you want to write it in terms of the lower degree invariants. So as I mentioned, we used Mathematica at one crucial step to get this matrix C that Catanova had produced a long time ago. So it's an 84 by 84 matrix. It then depends cubically on the entries of this tensor wedge 3 in wedge 3C9. And the trace of the powers of that matrix give the invariance. So numerically speaking, if you have the 84 by 84 matrix given to you, just store that matrix. You plug in the coordinates of your tensor, so you get a numerical matrix. You can then quickly compute powers of that matrix and compute the trace. So that's something that you can quickly evaluate. It turns out the invariant ring is generated by invariants of degrees 12, 18, 24, and 30. And then you could ask, well, how many monomials are there in degree 120? You might expect like 10 to the 58 monomials because you have a polynomial of degree 120 on 84 variables. That's ridiculous. There's not like enough particles in the universe at some point to just store these monomials. Well, in fact, though, there are only 28 monomials of degree 120 in these invariants. So just think about how much of a reduction that is. And you can just do standard linear interpolation with rational arithmetic to give the 28 coefficients of this discriminant, and this is what it looks like. Okay, so we can, oh, I almost fit it on one slide. I promise you I didn't hide very much at the bottom of the slide here, just the denominators of those fractions. That was kind of cool. We got confident that we could be able to, like, here's the first time you can evaluate this hyperdeterminant on any form. You don't actually have to do the Jordan decomposition to evaluate the hyperdeterminant for these wedge elements in wedge 3C9. You could just compute the values of the discriminants, I mean the invariants, F12 to F30, and then plug them into this formula. And then you get the value of the hyperdeterminant. Just one warning, and one of the coefficients is 1. That's by our choice to make the thing monic, but you didn't have to do that. You could make integer coefficients if you wanted, really. But if you do that, then the conditioning of the polynomial is a little strange. You have different orders of magnitude coefficients all around, but that's what we get. We can't change that. Okay, so we can compute really large invariants by this strategy. So we tried again. In the next case of E7, restricting to wedge 4, C8. This ring of invariants, though, is generated by 7 invariants of the degrees 2 up to 18, and we can still use the strategy of Catanova to find a matrix whose traces of powers give us the invariants. So we do that in any system that can store this matrix A. You can compute the traces of the powers. And I just gave you the example in Macaulay 2 code just to show you how simple it is to make the matrix and actually compute its traces. Just a few lines with a couple of things that are nice in Macaulay 2. You can tell it that the variables are skew commutative, and it knows the basis and puts everything in the right order so that the matrices that I want actually match up correctly. Okay, so we can evaluate these invariants quickly, but unfortunately, there's still 16,000 monomials of degree 126, which is the degree of the invariant we care about. We still get a speed, a reduction from maybe 10 to the 53 monomials if we're just looking for any polynomial in that space. But still 16,000 is large. So to find the coefficients of the monomials and the invariants that give you this invariant, well, you have to solve, to do linear interpolation of the rationals, you have to solve for the null space of a 16,000 by 16,000 matrix with rational entries. And that's a very challenging problem. I had always heard that reduction mod P was useful, and I believed it, but I never tried it before this paper. So we tried it. We reduced this computation to computing over 1,000 different primes, or sorry, 100 different primes over a value of 1,000. And then we could just parallelize the computation for for linear interpolation. So just with a very, very basic shell scripting and copying and pasting a Maple input file, I could change the parameters in the beginning and send the Maple computation to 1,000 different cores of the computer. Each process took 4 hours, but we did them all at the same time. So I have a cluster at Auburn that can handle that, and I was really proud to learn how to use this computational trick of reducing mod P. We still have to do not CRT, but Chinese remainder theorem and rational reconstruction to find the rational coefficients from their reductions mod P, and we have to certify that the reduction mod P linear algebra is actually correct over the rationals, and you can do that when you have done the reduction modulo enough primes. Okay, so once we do that, we get a polynomial with extremely deep rational numbers as the coefficients. Like the numerator of that rational number doesn't fit on one line, but that it is what it is. Those are the coefficients, and there's 16,000 of them. Actually, almost all of the monomials were non-zero. Notice the difference here: 15,976 versus just a few of them were zero. Almost every monomial that could occur actually did. Okay. All right, so we computed a really large invariant, and now if anybody wants to evaluate the hyperdeterminant for 4 vectors on an 8-dimensional space, just evaluate the invariants very quickly, plug them into this polynomial in the invariants, and you have a quick evaluation method for this polynomial. Okay, so the main theoretical tool is very densely worded, but essentially you just have to check one condition. If you want to take a vector space and split it into 2 pieces, and think about the hyperdeterminant analog for the big vector space projected down to the small vector space. You will get this divisibility of invariance as long as something we call the tangency condition is satisfied. That means that whenever you have a smooth point upstairs, the tangent space projects down into the tangent space downstairs. If that happens, and that's something you can try to check, then the dual variety for the smaller space lives in the restriction of the dual variety upstairs, and this gives us divisibility of hyperdeterminants in many, many cases. So that's the main theoretical tool. And I think that I don't need to do all the slides. Anyway, the rational map that we have that's projection actually satisfies the tendency condition. So whenever you look at the projection of your variety to a smaller space, well, the dual variety of that projection will be inside of the restricted dual variety upstairs. And that can be a key to finding expressions of these invariants. Okay, so I think I'll just leave it at this very complicated polynomial, and I'd be happy to entertain questions.
Sure. Thank you very much, Luke. That's indeed. I was kind of thrown back to my days doing Lie algebras and all these kinds of things. So it's great to see that connection. So questions, comments. As usual, I have a couple, but I'll give the chance to everyone to voice their minds. Let me see gallery view again. Okay, in that case, I'll go ahead and ask. I mean, this is perhaps extremely rudimentary and pedestrian compared to the heights of sophistication that you've attained in with these methods. But when so I'm thinking, I'm still at the slide where you define the determinant, the hyperdeterminant, in terms of. So maybe if you go back to this one, with the three, that's the one. I was trying to understand in what sense, how should I interpret this tangent space? And the fact that you take 1 point as rank 1 and then the tangent to be the. Can you elaborate a bit?
Okay, I can easily answer that for you. Yeah. So let's just take a point on the Segre variety. Mm-hmm. Is like this. It's something like A tensor B tensor C. And then from freshman calculus, if you try to take the derivative of this, you use the product rule with right. Use the product rule, right? So you get A prime B C plus A B prime C plus A B C prime with tensor products in between, right? And then you say, for the tangent space, I allow A prime to be anything.
Sure.
B prime is anything, and C prime is anything, and so this tangent space. Here's the
right.
So the tangent space at ABC of the Segre of PA cross PB cross BC is equal to A tensored with BC plus little a tensored with B tensored with C plus A tensor B tensored with big C. Okay? And that's this space here where, anything, think about what these are. All of the indices are Hadamard distance 1 away from this one. So if this is 0, 0, 0 at this index, then this would be like 0, 1, 0 and 0, 2, 0, and maybe this is 1, 0 or 2, 0, 0, 1, 0, 0. So they only differ in one spot. So then this one would be 0, 0, 1, 0, 0, 2. So like this line, I think about this line as A tensor B tensor big C. And then this line is like A tensor B tensor C. And then this one would be A tensor B tensor little c.
Yeah.
So those are the vector spaces that come up as the tangent space of the Segre. And then it's just the Euclidean inner product complement of that space to get the tangent hyperplanes. So then I have to imagine that each one of these tensors that I can get by altering the stars in the hypermatrix, they all annihilate a tangent space. So any hypermatrix, I put all zeros in red, and then everything else could be anything I want. It will annihilate this tangent space by the inner product pairing between the two, standard inner product. And so therefore that hyperplane will be tangent to the Segre. And so that's the analog of points on the determinant, that any matrix that has co-rank 1 has a vector in its kernel, in its right kernel, and a vector in its left kernel. And the fact that you have a right kernel is like, the tangent, that tangent space to the Segre in the two-factor case is just a tensor little b plus little a tensor big B. Those are the left and right kernel vectors. Like when you look at things that annihilate that.
Right. So I'm trying to see if there's a connection with this notion of higher. So I'll just formulate the question because I'm sure that you have something to say about it. So is there some known connections between hyperdeterminants and higher-arity Lie algebras that you know of?
The ones that I told about, essentially the things that I know of, which is when you can put your tensor into a Lie algebra in the way as a direct sum end, where the group that acts on the tensor has the Lie algebra of that group as part of the algebra you put your tensor space in, then the hyperdeterminant is the equation that defines the dual of the adjoint orbit of that Lie algebra in the appropriate space.
Right.
And so there's like that kind of uniform description. Unfortunately, or fortunately, the things that you would do after this are usually not Lie algebras. So that's what our current research is about, is like, well, what if you don't have a Lie algebra? What of this story can actually continue? And some things can continue, and that's what this exterior extensions package that I wrote is about, where the adjoint operator associated with the tensor is something you can still compute. And so you could compute the Jordan decomposition of the adjoint operator, and then think of the hyperdeterminant somehow as an invariant of that Jordan form. You can think about other invariants, not just the hyperdeterminant, that way as well.
Right. Yeah, I find it very interesting because I was reading some of your papers to try to get the sense of hyperdeterminant and connection to this higher-arity Lie algebras, because there seems to be some kind of interplay that is obscure to me to this day, where this notion of skew symmetry, when you push it up in order in several ways, it starts to kind of twist, and it starts to sort of become less rigid in a way, or it gives. So one of the main examples for people, I think there will be a talk that will mention on Friday that will mention higher-arity Lie algebras, but there is one of the main examples of these higher-arity Lie algebras are the so-called affine Filipov algebras, which are the ones that you just basically get by generalizing this, the high school determinant formula for the cross product, right? When you go to in dimension 3, you have the actual cross product for R3. When you go to dimension 2, you have the complex structure of the plane, of the real plane, and then when you go to dimension 4, you get some ternary operation that happens to satisfy the generalized Leibniz rule, right? So the generalized Jacobi identity. So you have a similar the similar concept that so the bracket is always an inner derivation, right? So you always have inner derivations. So I've been, one of the reasons why I'm asking this, and where maybe we could have a more detailed conversation at a different point, is that when you want to, so an open problem that we have, I mean, the people have had for some time, and we've had for some time, is that we want to recover these higher arity Lie algebras, which satisfy this extremely natural Leibniz identity, right? Sorry, Jacobi identity, right? I mean, it has nothing to do with symmetry. It's just a natural derivation property, right? And what we've been trying to do for some time, and people also failed in the past to do, has been to try and define some form of hyperdeterminant-like formula where from matrices, from 3 tensors or something like that, from higher order matrices, you get one of these higher arity Lie algebras. And there's been some very partial results that kind of do this with the trace and some combination, but there hasn't been anything as clean as you give me matrices, then you construct the commutator, and then you get a Lie algebra. Right? It's a completely universal construction. It's completely clean, right? I mean, matrices have an associative operation, and then you have the symmetrization and anti-symmetrization. It's a very clean story. And something similar for order 3 or rank 3 the tensors and higher has not been discovered. And one of the suspicions that I have is that the symmetry treatment of these higher order tensors is somehow richer. It's richer than what normally symmetry and anti-symmetry does, right? So in the following sense, so normally you have your positive and negative symmetrizations, right? I mean, you basically are weighting your tensors by 1 or -1, and you're using the fact that these are multiplicatively they are a group, but they also cancel inside the field, right? So if you extend this to a ternary operation, in a binary operation, you only have one possibility: symmetry or anti-symmetry, right? But when you go to a ternary operation, then suddenly you have richer symmetry. You have S3, like all the 6 symmetries, right? So you have subgroups of that and so on. And I have a feeling that, so for example, if you try to do cyclic symmetry, set 3 symmetry, you have the complex numbers with your cubic roots of unity give you a good instance of that, because they add up to 0 and they are multiplicatively a set 3. But what we don't have available as an algebraic tool is a field of numbers that will have 6, so a faithful representation of S3 that in which every element cancels out in the group of 6, but they don't cancel out in pairs or in trios, right? So that's kind of a missing piece that I have a suspicion that it might be one of the 3-dimensional associative algebras, for which there are, I don't know, like a bunch, not many, like 10 or 12 classes of those. But we still don't have that, and I feel like there's something to do with higher order determinants and invariants that is all muddled up there. So do you have any ideas, any thoughts about this kind of?
Yeah, I didn't have this slide in this talk, but there is I think I posted it to our website on Jordan decompositions of tensors, where when you start to ask whether there could be a Jordan decomposition, you want to ask whether there exists a binary product on your space of tensors, but you have a few extra things that you would like to have that go along with it, which are, one, that you preserve the tensor structure, and in a 3-line proof you can show that most tensor formats don't have a binary product that satisfies the things that you want when you don't expand the space to something larger, okay? And we also talk about in that paper, like, this idea where you take let's say of these 3 examples that I put here, you try to do the same thing. You say you have your space of tensors, call it M. This is my tensor space.
Right.
And like G is the group that preserves the tensor structure. So it'd be products of SLNs, for instance.
Sure.
And then say G is this Lie algebra. And then we just put G, and we arbitrarily take the outer direct sum of these 2 things. And then we may need to add some more things onto this. We attempt to define a bracket.
Right.
But we want the bracket to be G equivariant.
Sure.
And it turns out that there exists a G equivariant bracket only when certain conditions are satisfied. In particular, you need the tensor product with M and its dual to have a copy of G. And there's a few other things that you have to have. And once you start listing those, even for things like M equal to wedge K of Cn, we did this we completely handled this case.
Mm-hmm.
Then many cases, there just does not exist an equivariant skew symmetric bracket.
Right.
There's none. The only one is zero, the zero bracket.
Mm-hmm.
And in some cases, the only bracket that's interesting that exists is the symmetric bracket,
Mm-hmm.
where, AB minus, plus BA is the bracket of A and B, right? Like
Right.
that bracket. And so we're very interested in the same question of when could you use this construction to produce just which algebra do you produce? It can't be
Exactly.
a Lie algebra in many
Yeah.
cases, but it could be some algebra that other people have already studied, and then that gives you a way to think of your tensor in this larger space where there is a Jordan decomposition, where there should be one. At least there's one for the adjoint operators because we have matrix Jordan decomposition there, and we could ask whether that Jordan decomposition is consistent with the one that we would like to have for the tensor space.
Right.
And this business of the Cartan that I was talking about, it kind of tells you, there's some structure in the Cartan that's determined completely by combinatorics, and
Mm-hmm.
We're studying that condition as well to see, what combinatorial obstructions there might be to having the structure you're asking for. But like if you just, if you take A tensor B tensor C and you want to know, is there a bracket, then you're asking, is there a map like this?
Mm-hmm.
And you can sort of dualize all of this and imagine this is just the tensor product of these things dual
Sure.
to there. And now you're asking for an invariant tensor in this space. If you want to have an invariant product from ABC to ABC and ABC to ABC, then you have to have an invariant tensor in this space. And most of the time, there's not an invariant tensor in the space. So then you don't have an equivariant product that preserves the tensor product structure. It just doesn't exist. And so you could try to make your tensor space bigger. That's the only hope.
Yeah. Now, this is super interesting because one of the possibilities that I'll hope to explain on Friday that will have this higher arity possibilities allow is that you don't have binary operations, but you might have higher, like ternary or quaternary operations that and it opens up this larger realm of possibilities. So anyway, this is super interesting.
I guess one final comment I could make is just count dimensions. If you have SL, K, N, and you're acting on wedge K of Cn, in order for there to be finitely many orbits, the dimension of the group has to be at least the dimension of the space.
Sure.
And so this is, n squared minus 1, but this is n choose k, right? So n squared minus 1 is going to be much smaller than n choose k most of the time, except for these cases which I listed, where it's very close. And the difference in the dimension is actually this dimension of it's the number of parameters I was counting for the semi-simple elements.
Sure.
So, and these are the cases where we have a classification, even though there's not finitely many orbits, we still have a classification of orbits, and these are like the last in the series where there's such a classification. But what you said about these higher arity skew symmetric tensors, like becoming more twisted, this is in my mind, the real sense in which they become really more twisted is that the group is so much smaller than the space at some point that even acting by the group, you still have a very large space. In wedge 3 C9, there's only finitely many orbits, and so the group is much bigger than the space, and there's really almost no flexibility at all. But once you go to wedge 3 C9, there's flexibility, but it's under control. These are considered the tame cases. There's only finitely many parameters you need to describe the semi-simple part. But then after that, everything is expected to be wild. Right. There's not finitely many decompositions, and it really reflects this idea that you were saying, that there's just everything is much more twisted.
Yeah.
The natural group that's acting is just too small to like put everything under control.
Yeah. That's interesting to see this pattern sort of pop up in different guises. Yeah, very interesting. Anyway, any final comments or questions? So in that case, I think we can leave it there for today. I just was contacted by Edina Gang. He mistook the time zones, so he apologized. So we have now rescheduled for Friday. So I'll just send an email for the speakers, and the people here will also get it on the Discord. But basically, we'll reconvene on Friday. During the week, we're going to try to sort of self-organize some discussions. So you can either be on the Discord and leave links to papers and all kinds of information there. But otherwise, I imagine all of you have my email. You can just email me, and we can arrange something informally. So if there's nothing else, I'll see you during the week or on Friday. Thank you very much.
Thank you.
Goodbye.
Thanks. Cheers.